Hi everyone, welcome to PrepFusion. So now we are going to study about MOSFETs, metal oxide semiconductor field effect transistor. You already know what is MOS, but now you need to study about FET. What is FET? Field effect transistor. So we will study that, but let's see what we have already studied in the whole EDC. So first we started with the basic semiconductor physics, right? Then we studied PN junction. In PN junction, first we studied PN junction under equilibrium. Then we studied forward biased and we studied reverse biased, right? Then we studied BJT and then we studied MOSCAP and now we are going to study MOSFET. Now there would be few guys who will be studying right from the beginning, who have studied EDC completely. But a lot of guys would be there who have studied just basic semiconductor physics, then we studied PN junction under equilibrium, then we studied MOSCAP and now they are studying MOSFET. Now a few concepts from here and a few concepts from here will also be required to study MOSFETs. So first I will cover these concepts. So those who never studied these concepts, they will surely watch this video for next 30 to 40 minutes. Okay. Those who have already studied, they also need to watch it because some different conclusion we are going to make. So those who have already studied, they also need to watch it, but they can watch it in a quicker manner. In a very quick manner, you can watch it. Is that understandable to you? Okay. So at least you need to have a basic idea of basic semiconductor physics. You need to have a basic idea of PN junction under equilibrium and you need to have a basic idea of MOSCAP. Then only you can study from this particular chapter, and I hope everyone has done at least this much of part. Some guys are studying right from the beginning, so for them it will just be a revision, and those who did not study forward bias, reverse bias or BJT, for them it will be a new thing and they will be able to study a new thing as well. So it's up to you how to utilize the next 30 to 40 minutes. In next 30 to 40 minutes we are going to discuss what we have already studied. Well and good. So have we studied PN junction under equilibrium? Yes sir. Can you draw this Venn diagram? Surely. What is happening here? Sir, there is a depletion region. Holes try to diffuse from P to N and electrons try to diffuse from N to P and depletion region was made. Now what is happening, sir? There is a built-in electric field that has been developed. Now these holes will say that because of the concentration gradient we will try to diffuse, but built-in electric field will say go back. So drift and diffusion are equal to each other and total current is zero. So basically this much of barrier is making sure that drift and diffusion are equals to each other. Okay, so this barrier is making sure drift and diffusion are equals to each other and total current is zero. So this is your PN junction under equilibrium where total current is zero. This we already know, right? Now what we do, we give it some bias. So there are two kind of bias, forward bias and reverse bias. What are the names? Forward bias and reverse bias. What is the meaning of forward bias? So meaning of forward bias is P should be connected to positive, P should be connected to positive, N should be connected to negative. And what is the meaning of reverse bias? Sir, P should be connected to negative, N should be connected to positive. Okay. So this is the meaning of reverse bias. Now in forward bias, what will happen? Sir, this was my PN junction under equilibrium. There was a built-in electric field that was set up here. Built-in electric field was set up in this direction from positive to negative. Now the external battery that you are applying, that will make the electric field to be set up in this direction. Say yes or no? The external battery that you have applied, that will make the external electric field in this direction. Say yes or no? Because this will be positive and this will be negative. So this will be the direction. Now there is one more important thing. What is that? This is your neutral P region, right? And this is your neutral N region. We call it neutral P. That means here there are enough holes. Here there are enough electrons. But in the depletion region, there are very less electron and holes, right? That means depletion region will have higher resistance. Why higher resistance? Because there are lesser electrons and holes. There are lesser charge carriers. Less charge carrier means less conductivity. Less conductivity means more resistance. Is that clear to you? Sir, here more than enough holes are there. Here more than enough electrons are there. That means they are having good conductivity. Good conductivity means less resistance. So this particular part will have less resistance. This particular part will have less resistance. Now this particular part is having very less charge carriers. Less charge carrier means less conductivity. Less conductivity means more resistance. So the in between part would be having more resistance, and again this will have lesser resistance. And now you are applying this VA. What you are doing? You are applying this VA. So what will happen is that whatever the potential that you are applying, whatever the potential that you are applying, most of the potential will be dropped across the depletion region only. So if I am applying this VA, most of the part will be dropped here only. Is that understandable to you? Because this depletion region provides a very high resistance. That means whatever the external bias that you are applying, that will be dropped across that depletion region, most of the part. That means this external field that has been set up, which will be mostly set up in this much region only. This is your E external. Now E built-in and E external are opposing each other. E built-in and E external are opposing each other. That means the depletion width will become smaller because electric field will become smaller. This guy and this guy both are in opposite direction. That means they are opposing each other. That means effective or total electric field will become lesser. That means depletion width will become lesser. So this depletion width will move. This will move here, and this part will move here. So yes or no? And here you will get the holes. They will get back their holes, and they will get back their electrons. So effective depletion width has reduced. This effective depletion width has reduced. So in forward bias, effective depletion width reduces, right? In reverse bias, what will happen? Sir, already built-in electric field was in this direction. Now, sir, this part would become positive and this part would become negative. Why I made positive here? Why not here? Because I told you one thing, this particular part is neutral. This particular part is neutral. So this will have very low drop. So whatever the positive potential you are getting here, the same kind of positive potential you will get here. Whatever the negative potential you are getting here, the same negative potential you will get here. That means this will be my external electric field. Both are supporting each other. Both are supporting each other. E built-in plus E external. Both are supporting each other. That means depletion width will expand. Arey bhai. Depletion width will expand. Okay. So they will lose their holes. Someone would be thinking that, sir, from where these holes came? From where these holes came? From where these electrons came? From the battery. Okay. Battery supplied these holes. Okay. Battery supplied these electrons. And someone would be thinking that, sir, where those holes go? Like where these holes went? You are saying that, sir, they will be losing their electrons. They will be losing their holes. So where they are going? They are eaten up by battery. Arey yaar. Okay. So what really happened was electrons started traveling here and those holes were eaten up by these electrons. Holes started traveling here. Those electrons were eaten up by these holes, right? So battery is doing everything. Because of the battery, built-in electric field, this external electric field and built-in electric field both were in the same direction. So depletion width got extended. Here depletion width got narrowed. Okay. Now what about the energy band diagrams? Sir, P side is being positive, N side is being negative. At P side you are applying positive, at N side you are applying negative. What did I tell you? When at a particular side, if I apply negative, the side goes up. Negative means side will be going up, and if I am applying positive, the side would be going down. So this was the scenario. Previously this was the scenario. Now what will happen? Under the forward bias, N side you are applying negative. That means this side will go up. And P side you are applying positive, this side would come down. So what will happen? This barrier will reduce. This barrier, this was your under equilibrium. Under equilibrium, this much barrier was there. This much was your barrier. This was under equilibrium. Now when you apply the forward bias, the barrier has reduced. The barrier has reduced. Can anyone tell how much will be this barrier? Yes, sir. Say, sir, it would be V built in minus V. Say yes or no. Barrier has reduced. Right? And what about the reverse bias? Sir, this side is negative, this side is positive. Wherever you apply positive, that side come down. Wherever you apply positive, that side would come down. Wherever you apply negative, that side would go up. So this side would go up when it comes to reverse bias. Sir, this side would go up and this side would come down. So what really happened? This side would go up, this side would come down. So that means barrier has increased. And what will be the new barrier? Can anyone tell? Surely a lot of people can tell. Sir, new barrier would be nothing but Q V built in plus VA. Okay, like in place of VA, we should write down how much potential is coming here. I said that most of the part of VA would be coming here. It's not that complete VA would be coming here, most of the part of VA. So here we should have written down how much part of VA is coming on the depletion region. Let's just say VF part of VA. VA was 3 volt and 2.99 volt came here. So in place of VA, we will write down 2.99. But in the examination, they will not give you this value. So by default, you will take 3 volt only. Is that clear? In the examination, you will say, sir, whatever the part that has been applied, the whole part will be coming across the depletion region. But some part would be coming, some part would be missing as well. And this point in a great detail we have discussed when we studied PN junction under forward bias and reverse bias. In very detail we have discussed, right? But as of now, what you will understand that, sir, whatever the potential that you have applied, complete potential is coming across the depletion region. Whatever the potential that you have applied, complete potential is coming across the depletion region. That's why I have put V built in plus VA, V built in minus VA. The barrier has increased here. Okay. Now let's discuss one more point. We are having two phenomena, right? Drift and diffusion. Do you remember why drift takes place and why diffusion takes place? So drift takes place in presence of electric field. If there is some electric field, then electrons will be moving here, holes will be moving here. Because of that, some drift current would be coming. So whenever I say drift, that means I talk about electric field. And whenever I say diffusion, I talk about concentration gradient. Concentration gradient. Now let's talk in which scenario drift would be more. What is the meaning of drift? Drift means electric field. Electric field is like an external force. Electric field is like an external force. Like this is like a force only. In diffusion, what will happen? Sir, here there are a lot of electrons. Sir, here there are lesser electrons. So those guys will move. This is your diffusion. But what is the meaning of drift? Drift will not look at the concentration. Drift will say that if there is an electric field, I will move. That's it. Now let's just say you are standing here, and in one scenario you are standing here. I push you by the force of 1 Newton. Here also I push you by the force of 1 Newton. In which of the scenario you will be rolling more? Rolling more means like you will be moving faster. In which of the scenario? Here and here. In both of the scenario, I am giving you same force. So if I push you by a force of 1 Newton, here what will happen? Sir, larger slope is there. So I will move faster here. But sir, here very less slope is there. So I will move very slow. Basically, sir, if you push me from here, then it might happen that, sir, because of the force that you have given, I may end up getting till this place. But sir, because of the force that you have given here, sir, here the slope is lesser. So it might happen that, sir, I end up getting till this place only. That means the effect of force is more in this particular scenario. Effect of force is more in this particular scenario. So here who is dominating? Drift is dominating. Is that understandable to you? Effect of external force is more dominating in the reverse bias. Here drift is dominating. Let's come to this scenario. Let's talk about the diffusion now. Let's just say you are standing here, and let's just say you are standing here. Okay, I ask you to go up, and here I ask you to go up. In which scenario you would like to go up? In this scenario or in this scenario? Surely in this scenario, because here you need to cover the lesser distance, here you need to cover the more distance. So in which scenario you would like to move on your own? In diffusion, what will happen? In diffusion, you will not require any external force. What will happen in diffusion? No external force is required. What these electrons will say? We will move on our own. On our own will. On our own will, we will be moving. You don't require any external force. So if you are standing here, this was your P side. This is your N side. In N side, there are more number of electrons. In P side, there are lesser number of electrons. More number of electrons, lesser number of electrons. That means these electrons will move from here to here. Say yes or no. This will be your electron movement. Why so? Because here the barrier is lesser, no? If you are standing here, on your own will where you will move, in this case or in this case. Sir, in this case, because sir, the barrier is lesser. So this particular scenario is diffusion dominant. Is that understandable to you? Let's remove these guys. So for the drift, what I explained, if you are standing here and I push you, then you will get the more force. So here your movement would be faster. And if I talk about the diffusion, you are standing here as well, you are standing here as well. Here you will say that, sir, there is lesser barrier. I need to climb up a lesser barrier only. I need to climb up only this much of path. But here I need to climb up a very high path. So I will prefer climbing up this particular path on my own. That means here diffusion would be dominant, here drift would be dominant. Is that understandable to you? So in forward bias, diffusion is dominant. In reverse bias, drift is dominant. Let's explain it with respect to physics as well. Now we will understand the physics. So previously, when your PN junction was under equilibrium, what was happening? Drift and diffusion were equal. Now what you have done? You have reduced the electric field. You have reduced the electric field. Now what this hole will say? I will try to diffuse. What this electric field will say? That I will not let you diffuse. This hole is saying that I will try to diffuse. Electric field will say that go back, I will not let you diffuse. But now the hole will say your potential, your electric field has become lesser than this electric field. Now your effective electric field has become E built in minus E external. Now you are not very strong. Previously you were strong. You were not letting me diffuse. Here this hole said that I want to diffuse, but what this electric field say? Go back. Here this hole is saying that I want to diffuse. Now this electric field will say go back, but hole will say your potential has reduced now. That means your capability has reduced. Your electric field has reduced now. Now I will surely diffuse. Similar thing would happen with the electrons as well. Electrons will also diffuse. That means diffusion is taking place in this scenario. Electric field has reduced. That means drift has reduced. Diffusion has increased. So here diffusion is taking place. Say yes or no. What about this scenario? Here holes will say that I will try to diffuse. Electric field will say go back. Hole said that I will try to diffuse. Electric field will say go back. Can this hole say anything to this electric field? No. Because this built-in electric field was enough to take him back. Now built-in electric field plus external electric field. This has become even stronger. So there is no chance that this hole can diffuse. There is no chance that this electron can diffuse. But because of this stronger electric field, there are some minority carriers, no? Here there are some electrons, here there are some holes. So because of this stronger electric field, some holes will be moving here and some electrons will be moving here. Because of this electric field. So they are drifting. This electron is also drifting. And this hole is drifting here, electron is drifting here. That means there will be a current direction. There will be a current in which direction? In this direction. That means in the wire there will be a current in this direction. Holes are drifting in this direction. Holes are drifting in this direction. Electrons are drifting in this direction. That means because of both of them, the current would be in this direction only. So there will be a current in this direction. Here what is happening? Holes are diffusing in this direction. Electrons are diffusing in this direction. What does that mean? There will be a current in this direction. So there will be a current in this direction. Is that understandable to you? Holes are diffusing in this direction. Holes are diffusing in this direction, and electrons are diffusing in this direction. That means the current will be in this direction only. Here what is happening? Holes are drifting in this direction. Electrons are drifting in this direction. So there will be a current in this direction. Is that understandable to you? So all this scenario, all this physics, everything is understandable to you. Now in which scenario the current would be more? In which scenario the current would be more? Here also there is some current, here also there is some current. Let's call this current as I1, this current as I2. So here the current is coming because of the minority carriers. Holes are minority, electrons are minority. Very less concentration is there. Inside the depletion region, very less concentration is there. So here the current is coming because of the minority. But here the diffusion is taking place. Because of that current is coming, and diffusion is happening with respect to majority charge carriers. Holes are majority here. Majority charge carriers are diffusing. Majority charge carriers are diffusing. So here current is coming because of the majority. So what do you think? Which current would be more? I1 would be more than I2. On a very top level we are studying, okay? It's not the in-depth explanation. In-depth explanation will take roughly around 6 to 7 hours or 8 hours as well. But we are going to cover in 20 to 25 minutes. So that's why on a very top level we are studying it. Still, most of the points which are required for your examination that we are going to cover. Okay, so I2 would be actually very low, and ideal case we will take it 0 only. Ideally we will take I2 current to be 0, ideally. Okay, and I1 current is good enough. So this is known as forward bias, this is known as reverse bias. In forward bias, sir, depletion width has reduced. In reverse bias, depletion width has become larger. In forward bias, diffusion dominant. In reverse bias, drift dominant. In forward bias, current is lesser. In reverse bias, current is more. In forward bias, the barrier has reduced. In reverse bias, the barrier has increased. Okay, and it is diffusion dominant. This is also half true. Like a lot of things are there which are not that important for your examination purpose, and secondly, not at all important for understanding MOSFET. For your examination, PN junction is not very important, but MOSFETs are very important. So just to make you understand the MOSFETs, we are studying all these things. Okay, forward bias, reverse bias, because again and again I will be using forward bias diode, reverse bias diode in MOSFETs. Okay, right? Now what is the circuit symbol? How do we represent PN junction in circuits? So this is your PN junction. So this is how I will be representing it. This is the symbol. Okay, this side will be P and this side will be N. Let's just say someone says, sir, NP you make. So NP I will be making in this direction, in this way. This side is N, this side is P. Is that clear? So this is how we will be representing NP, PN. All fine? So all the conclusion we have written. Forward bias, less depletion width, more current, diffusion is dominant. Reverse bias, more depletion width, less current, drift is dominant. Drift is dominant. Okay. So this is your depletion width under equilibrium. Do you remember the formula? Yes, sir. Under root 2 epsilon by q 1 upon Na plus 1 upon Nd, V built in. Depletion width under forward bias. What will happen? Depletion width will reduce. So here what should come? Plus sign or minus sign? Minus sign, no? Or you can see from here. So this barrier has become, in place of q V built in, we are putting V built in minus Va. So here which sign would come? Minus V. So like in the examination they can say that, sir, Va is equals to minus 3 volt. You are applying a forward bias of minus 3 volt. So does this minus sign matter to you? Here what you will put? V built in plus 3. No. You know that in forward bias the depletion width should reduce. If depletion width should be reducing, that means here something should be subtracted. That's it. So you need to subtract it. And here what will happen? It should be added. So never ever get, in EDC I have told you one thing, never ever get confused with the sign. Is that clear to you? Never ever think about the positive negative sign. You just need to know that what is increasing, what is reducing. Based on that you will put positive or negative value. If they are saying that forward bias of 3 volt is applied, reverse bias of minus 3 volt is applied, drop this negative sign. I only care about the magnitude. Now positive sign I need to use or negative sign I need to use, that will depend on my intuition. I know that, sir, forward bias depletion width will reduce, negative sign I will use. Reverse bias depletion width will increase, positive sign I will use. Well and good. Okay. Now you might be having a lot of doubt that, sir, what if V built in becomes greater than VA? Sorry, what if VA becomes greater than V built in? Let's just say, sir, V built in is 0.7 volt and I have applied VA equals to 1 volt. Then, sir, 0.7 minus 1, this would become negative, this would become my imaginary number. Then, sir, what will happen? So on top level I can tell you one thing, this VA will never ever cross V built in. Okay, whatever the bias that you apply, that will never be able to cross V built in. Have you heard the term of cut-in voltage? In your engineering life, in your college, you would have surely understood cut-in voltage. So people say that cut-in voltage is equal to V built in. Absolutely baseless. Cut-in voltage is a different concept, V built in is a different concept. So actually, the applied voltage, like I can apply 3 volt here, but wherever we are putting VA, actually we should have put VF, right? I told you this thing, that in place of VA, we should put whatever that depletion region is taking. So no matter whatever how high VA you apply, no matter if I go VA equals to 10 volt, 20 volt, 30 volt, 40 volt, this VF will always make sure that this VF will always be lesser than V built in, always. In a lot of lecture I have seen that if VA is more, then what it will do, it will cross the barrier, and then depletion width will be completely vanished. Depletion width will never be vanished. If there is a PN junction, surely there will be a depletion width, no matter whether you apply forward bias or reverse bias. All these points in great detail we need to discuss. But as of now, we are just seeing it on a top level, right? So whatever that is necessary for your examination, that would be covered from these slides only. Most of the chances are there that, like, higher chances are there that they would ask you depletion width in reverse bias. 9 out of 10 times, 9 out of 10 times questions have been framed from this formula. That's it. They will ask you to find out the V built in, they will give the reverse bias, and they will ask you what will be the depletion width. They can ask you the depletion width towards P side or N side. In that manner, they can ask you the question. So if you know the total depletion width, then you know that, sir, what will be the depletion width towards N side. So sir, depletion width towards N side would be W depletion multiply with Na upon Na plus Nd. So you find out this W depletion under reverse bias, then multiply with Na upon Na plus Nd, you will get the depletion width on N side. Similarly, you can find out depletion width on P side as well. So all these things you know. So most of the chances are there that if they ask any question in PN junction, they will ask PN junction reverse bias and this formula will be used. 9 out of 10 times. Okay. But yeah, a lot of in-depth things are there in PN junction as well when we talk about forward bias and reverse bias that we cannot discuss as of now. So whatever that we are discussing here, that is necessary for understanding MOSFET, and it will help you solving the problems of forward bias and reverse bias as well. That's why I thought that we should be discussing all these things so that confidently you can go in the examination. Even if you are covering not complete topic, even if you are covering PN junction under equilibrium and MOSCAP and MOSFET and surely your basic semiconductor physics, then also there is chance that 90% question you will be able to solve. 90%. If 5 questions are coming, 5 by 4 would be 80% actually. So 80% question you will be able to solve. After 4 questions you will be able to solve. This much of a strong basic we will build up. Don't worry about that. Okay. So yeah, if you are having any other kind of doubt, you need to hold on because you are not studying comprehensively, right? So that's what I was saying. So let's go to our BJT now. What is this bipolar junction transistor? This is known as BJT. I will be calling it BJT. Okay. So what we do in this one, I took a piece of silicon. I divided it into 3 parts. One part, and these are your 3 parts. Okay. Here in this particular part, I did the doping of N type. Here I did the doping of P type, and here I did the doping of N type. So what I have made NPN. So this is known as NPN transistor. What I could have done, I could have made it PNP as well. Okay. PNP was also possible, NPN is also possible. I have made it NPN. Is that clear? Okay. Now what I do, like initially, basically there are 3 nodes, right? This N region I am calling as collector. Why it is known as collector, you will understand. This particular N plus region I am calling as emitter, and this particular P plus region I am calling as base. Basically this line is connected to this guy, this line is connected to this particular guy, and this line is connected to this particular line is connected to this guy. So emitter, collector, base. Why these names are given, you will be able to understand. Don't worry. I want this collector current. Okay. Sir, you want this collector current, what do? Sir, you forward bias it, you will get the collector current. Sir, NPN you are having, no? So just forward bias it, you will get the collector current. So if I just want to make it forward bias, then I could have simply gone to PN junction only, no? Why I am coming to PNP? So what do I want? I want this collector current to be depending on this particular voltage. Whatever the voltage that I apply here, this collector current should be depending on this voltage. This is my target. My target is that my collector current should be a function of VBE, base to emitter potential. So what do I do first? First, let's talk about the equilibrium. What is the meaning of equilibrium? Sir, everyone is having 0 bias. No bias is there. No bias is there, no current would be there under equilibrium. So N plus P plus N. So this will be your N plus plus P plus and N. What is the meaning of P plus? Here there is good enough doping. N means, N plus plus means this is having highest doping, then second number this doping, and then third number this doping. Okay. So this guy is having the highest doping. This is the meaning of n plus plus, p plus and n. So these guys were separate available. This is your n plus plus, this is your p plus and this is your n, right? Now if I join them, what will happen? So current would be 0. Current would be 0. That means these Fermi levels will be inclining. What will happen? This guy will come down, or you can say basically this was the scenario. So what will happen? This guy will come down, this guy will go up and this guy will come down. Basically they need to come at the same level. So what I am saying, this guy remains as it is. So what will happen? This guy comes down and this guy also comes down. So this will be the scenario we will be getting. So this kind of Venn diagram we will get. Okay, and this will be absolutely flat. This will be absolutely flat. So what I do, I remove it and this would become absolutely flat. Is that clear to you? So this kind of Venn diagram under equilibrium you are getting. So here also there is some barrier and here also there is some barrier. What these barriers are doing? These barriers are making sure that drift and diffusion both are equals to each other. Now if I play with these barriers, if I reduce or increase these barriers, then something may happen. As of now, drift diffusion, here also drift diffusion would take place, here also drift diffusion would take place. Both are equals to each other and total current is 0 because there is no external bias, total current is 0. Now what do? I give it forward bias. Here I give a forward bias. Forward bias means N should be connected to negative and P should be connected to positive. N should be connected to negative and P should be connected to positive. So this is the forward bias that I have given. Is that understandable to you? And here what do? I give it a, let's keep it only the forward bias. This is the scenario, this is the bias that we have given. I will call this as VBE because B is at higher potential, E is at lower potential. So I am calling it VBE. Now what will happen? This barrier will reduce now. If you have given it a forward bias, this barrier will reduce. This barrier will reduce. If this barrier has reduced, then what will happen? Diffusion will increase. That means a lot of electrons from here to here, they will start diffusing, and a lot of holes from here to here will start diffusing. And because of that, current would flow. But this is like a simple PN junction under forward biased. We are not even using this one. We need to take help of this guy as well, no? Like if I am not taking the help of this guy, then it is simple like a PN junction under forward bias. I need to take help of this guy as well. Now I want you to think here what you will apply, forward bias or reverse bias. You want this collector current, right? You want this collector current. You want this collector current to depend on this voltage. Now what this voltage have done? This voltage have sent a lot of electrons in this P plus region from this N plus plus region. So this particular bias has made sure that from this N plus plus region, a lot of electrons have come into this P plus plus region. Now somehow if I make a very strong electric field here, then what will happen? Whatever the electrons that have come here, they will be pulled by this particular electric field. If this is the electric field, electrons will be pulled in this direction. So because of this very strong electric field, these electrons will be pulled in this direction. That means these electrons will be drifting in this direction. Here they have diffused. So what should I make it here? Reverse bias, right? If I make it reverse bias, then electric field will be very strong. What this side will be doing? Electrons will be diffusing. Just as electrons come into the base, this is known as base. Just as the electrons is coming into the base, what they will feel? They will feel a very high electric field and they will be swept away. That means here what I need to do? I need to apply a reverse bias. Sir, why not forward bias? Look, if you have applied forward bias, then this current IC would come because of the mainly forward bias only, no? Like if I had applied forward bias, then this electric field will not be strong. This electric field will be very weak. So what will happen? Holes will be diffusing here and electrons will be diffusing here. So here this IC current would be because of the holes diffusion and electron diffusion. And this is not I want. This is not something that I want. I want this IC to be a function of VB. How will I make it? Sir, you applied VB here. Because of that, a lot of electrons are diffusing from this N++ region to P+ region. A lot of electrons have come here. Now, what these electrons needs to feel? These electrons needs to feel a very high force so that these electrons are swept away in the collector region. And because of that, the current would flow. Although electrons are swept away in this region, so current IC would flow in this direction. The direction of IC current would be this, because electrons are moving in this direction, so current would be opposite. Is that understandable to you or not? Is the working clear? Why I made it forward bias, why I made it reverse bias, is that clear? I will call it VCB. And this combined voltage, what I can call it? This combined voltage, or let's show the positive sign here and negative sign here. This combined voltage I can call as VCE, because this is at higher potential and this is at lower potential. So VC I can call it, or just forget about it. Don't care about it. So here I have applied forward bias. This is known as emitter junction. And why it is known as emitter? Because it is emitting the electrons. Why it is known as collector? Because it is collecting the electrons. So why it is known as base? So it's like in the base, electrons are staying. It came, it stayed here and then pulled away. So this is known as base. Emitter, base, collector. Base is the middle point. Like base is common to collector as well, base is common to emitter as well. So this is known as your emitter junction. This is your emitter junction and this is known as your collector junction. So this is your emitter junction, this is your collector junction. Is that clear to you? So here I have given the forward bias, here I have given the reverse bias. By the Venn diagram as well we will understand, but physics is clear to you. Here they will diffuse and then here they will be drifted and good amount of current would flow, and this current would be surely a function of VBE. Okay, and the relation would come out to be IC is equals to I naught e to the power VBE by eta Vt, where Vt is the thermal voltage, right? I naught is known as reverse saturation current. You don't need to care about I naught. I naught is as some fixed current. Okay, it is known as reverse saturation current. What is Vt? You already know. Thermal voltage. Arey yaar, why I am making like this? I naught is reverse saturation current. Vt is thermal voltage. And VB you already know. That's it. Or what is neta? Neta is known as ideality factor. So it can have a value of 1 or 2. It could be either 1 or 2. If nothing given in the examination, you will take it 1. If it is given, you will take it 2. Okay, so this IC is depending on simply this VB value, and this relation would come out. How this relation is coming out, that you don't need to care. Big derivation is there that we are not going to do here. Working is clear. Let's understand by the Venn diagram. So here what I have done, I have applied a reverse bias, and here what I have done, I have applied a, here I have done a forward bias and here I have applied a reverse bias. So this barrier will increase. This barrier will increase. Or you can understand from here as well that sir, you are applying positive here. If you apply positive here, that means this guy will go down. And sir, here you are applying negative. What is the meaning of negative? Meaning of negative is, sir, this guy would go up. So this guy is going up. That means this barrier has reduced. This guy is going down. That means this barrier is increased. So this kind of diagram you will get. This barrier has reduced. And this barrier has increased. Right. So what is happening? This was your N plus region, right? This was your P plus and this was your N. So a lot of electrons from here to here has diffused. Right? And because of this high electric field, they have simply went down. And because of that, this current IC has flown. Is that understandable to you? So this is a good setup that I will reduce this guy and I will increase this guy. Then I will get a good high current. Now let's just say if I did not apply this VB, if this VB was not there, only I made a reverse bias, then what would have happened? then sir, this barrier would have increased, but this barrier would remain as it is. What I am saying, I am not applying this VB, I am only applying this VCB. So if you only apply this VCB, which is reverse bias, then this barrier will increase, but this barrier would remain as it is. If this barrier is remaining as it is, that means no electrons would be coming from here to here. What I am saying, this is not there, only this guy is there. That means this barrier would remain as it is under equilibrium. This barrier would be under equilibrium. But what would happen with this barrier? This barrier would be increased. That means whatever the electrons that are coming from here to here, this would not come. Only some reverse bias current would flow. Basically, it would simply act as a PN junction under reverse bias if this guy was not there. It is simply your PN junction under reverse bias, and in reverse bias the current would be very less and IC would be nearly zero. But because of this VBE, a lot of electrons are coming here and they are being swept away. Because of that, good amount of current is coming. So you can directly see that this IC is directly depending on this VBE. Is that understandable to you what I am saying? Okay. So this forward bias is also required here, and this reverse bias is also required here. This reverse bias is making sure that here, if a lot of electrons are there, they can easily drift. Here they can easily drift. Electrons are easily drifting. Electrons are easily drifting. This increased barrier is saying that electrons are easily drifting, and this reduced barrier is saying that electrons are easily diffusing. So electrons are diffusing in this direction, drifting in this direction. That means there will be a current in the opposite direction, which will be IC current, which will be your collector current. Clear? Right? This barrier reduced, this barrier increased. So it's like they go here and then they went down. Well and good. All fine. So this is about a prerequisite that we have done in 40 minutes. Okay. Another prerequisite is there. We will compare the N plus P junction and N plus N junction. Basically here, let's just say the doping is 10 to the power 18 donor atom, and here the doping is 10 to the power 16. Here also the doping is 10 to the power 18. Here the doping is, let's just say, 10 to the power 14. Here let's just say doping is 10 to the power 18, and here the doping is 10 to the power 16. Here it is donor, donor, donor. This is also donor. This is also donor, but this is acceptor. And this is your donor, and this is acceptor. Right? You understand the meaning of P minus, although P minus we don't use. Right? But here I have put P minus. That means you need to say that, sir, this doping is more than this doping. So under equilibrium, what will happen? Sir, under equilibrium, both of the Fermi level will incline. So both of the Fermi level will incline. This will be the scenario. Conclusion is important. Whatever the conclusion that I say, that is important. So no current would flow under equilibrium, but whatever the conclusion that I am going to make, that is important for you. Here also the same scenario would happen. And here also the same scenario would happen. Right? So if I say this barrier is QB1, this barrier is QB1, okay, this barrier is QB2, and this barrier is QB3. So can you say one thing, that sir, B1 is greater than B2 is greater than B3? Here I should have written, yeah, 10 to the power 16 is fine. Okay. What you understand from here? That sir, N plus and P, they are very different. They are very different from each other. No? N plus is and P. He is saying that I am having 10 to the power 16 holes, and he is saying that I am having 10 to the power 18 electrons. That means they are very different. So two different guys will have higher barrier. Now they are also different, but these two are more different than these two guys, right? This is having 10 to the power 6 electrons. If I say Ni equals to 10 to the power 10, then at least this is having 10 to the power 6 electrons. This was having 10 to the power 4 electrons only. So they are also different. They are also different, but they are very different. So if more difference is there, that means more barrier would be there. They are very less difference. He is saying 10 to the power 18. He is saying 10 to the power 16. That means very less barrier is there. If both were same, then there will not be any barrier, right? So this point we have already discussed, just to make you remember, because somewhere I am going to use it, that n plus n will have lesser barrier than n plus p. This is the line that is important. What is the line? That n plus n having less barrier than n plus p. This line is important. Somewhere I will use this line. Okay. So let's get started studying about MOSFETs. So we will study about MOSFET, but have you seen this kind of thing in your homes? Yes, sir. This is a tank. Here there is a tap connected, right? So what will happen? When you turn on this tap, water will come from here and it will flow from here, right? So it's like a source of water. Say yes or no. Can I call this as source? It's like a source of water. And here water is being drained. So can I call it a drain? Say yes or no. It is like a source of water. Here water is being drained. So I am calling this as drain. Now there is something called gating. In electronics, you will always hear the word gating. What is the meaning of gating? Gating simply means controlling. Sir, I am gating this particular circuit. Let's just say you designed a particular circuit. In this circuit, what is happening? When you give the input 1, it gives the output as hello. Okay. And when you give it input 0, it gives the output as bye. Now someone is saying that gate this circuit. Gate this circuit means I will put a enable button here. If I put enable equals to 1, then it will work perfectly. But if I put enable equals to 0, then it will not even work. Whether you put 1 or 0, it will show the output as error. That's it. Gating means controlling. If you are gating this particular circuitry, that means you are putting another pin that will control the output. So it's like a gate only, no? Because if I turn on the tap more, then more water will flow. If I turn it on lesser, then less water will flow. If I don't even turn it on, then water will not even flow. So it's like a gate. This is the source of water. Here water is being drained, and this is like a gate, which is gating the flow of water. Gating means controlling. Okay, in digital electronics, we use it like we are gating this particular circuitry. Gating this particular circuitry means you are actually controlling the output. And how do you get it? You get it using the NAND gate or AND gate, right? Because NAND gate, what it will do? If I say this is my enable button, so if I put enable equals to 1, then whatever the output was here, the same output would come out. But if I put enable equals to 0, then output would be 0 only. So you always do the gating using the AND gate. Okay, or you can use the NAND gate as well. So that's a digital electronics thing. We are not going there. Yeah, as of now, these things are clear. So source is clear, gate is clear, drain is clear, right? And picture credit from dreamstime.com. Let's understand the MOSFETs. So let's design a MOSFET. What I will do, I have taken a p-type substrate. Don't look here, only look on this slide. What I have done, I have taken a p-type substrate. This is completely p-type, p-type, p-type. Now what I am doing, in some particular region of this p-type, what I am doing is that I am doping n plus region, and here also I am doping n plus region. In the p-type, in this p-type substrate, some portion I have doped with donor atom, some portion I have doped with donor atom. Okay, fine. Then what I did, then I put a layer here, this layer is of oxide, this is a oxide layer, and then over this I have put a metal. What I have done, over this I have put a metal. Now this particular node I will call as gate. This particular node I am calling as drain. And this particular node I am calling as source. Okay. And another node I am defining, which I will be calling as body. This is my body. So till this particular thing you have seen, right? metal oxide semiconductor, p-type substrate. So MOSFET you have already seen. What is the different thing we have done? Just sir, here you have done the doping of N substrate. Sorry, I should not say N substrate. You have done the doping of a donor atom. Here also you have done the doping of donor atom. You called this node as drain. You called this node as source. So source is connected to N plus. Source is connected to N plus. Drain is connected to N plus. And body is connected to P substrate. Body is connected to P substrate. When we made NPN, there I said that emitter is connected to N plus, base is connected to P, and collector is connected to N. So similarly, body is connected to P, source is connected to N plus, drain is connected to N plus. And then there is a gate as well, there is oxide as well, and then there is this substrate as well. Now let's go back to this picture. Here water will be flowing like from which path? That from here water would come and it will be flowing like this. So this is the path of water flow, right? So can I say this is the channel of water? This is like a channel, no? The water is flowing from this particular channel. Channel means from where, from which path water is coming. So in our MOSFET, we will call this much part as channel. Okay, this is our channel part. This is our channel part. We call it channel. So we are having 4 nodes, or better we can call it, we are having 4 terminals. What we are having? We are having 4 terminals. Source terminal, gate terminal, drain terminal, and body terminal. So 4 terminals we are having. In BJT we were having 3 terminals, right? Emitter, base, collector. Here we are having 4 terminals. Gate, source, and drain. What will be the use of gate? It will be controlling. Controlling what? It will be controlling the current flow. Or better I should say, it will be controlling the charge carrier flow. What will be the use of source? From source, charge carrier will go out. From source, charge carrier will go out. Then they will travel through the channel and they will get inside the drain. From the source, water is flowing out. They will be controlled by the gate and flowing out of the drain. From the source, electrons will go out, travel through the channel, will get out of the drain. What is electron here? Electron is the charge carrier. And what will be the use of gate? Sir, gate will be controlling. How it will be controlling? We will see that. Similarly, can you make the N-type substrate as well? Yes, sir. We can make the N-type substrate as well. There is no doubt about it. We can use N-type substrate, and in the N-type substrate, what we will do? We will do the doping of acceptor atoms. Acceptor atoms doping we have done. And then again, sir, the same thing I am going to do. Ditto same thing I am going to do. Oxide layer, sir, and over that, sir, metallic plate. So metal oxide semiconductor I am having, MOS. Let's give the naming to the nodes. This is source, this will be your gate, and this will be your drain. Source, drain, and gate. And this is your body. Okay, right? And this will be your channel. What will happen? From the source, charge carriers will flow out. It will travel through the channel and then it will get inside the drain. What is this charge carrier? These are holes, which are charge carriers. Here the charge carriers are holes. Okay, well and good. Right? So here who is contributing in the current? Like electrons is flowing, right? And here holes are flowing. Here electrons are flowing, here holes are flowing. So here holes will be contributing in the current and here electrons will be contributing in the current. So this is known as NMOS. The name is NMOS. Okay, what is the name? Name is NMOS. Why it is NMOS? N stands for electron. P-type substrate, but the name is NMOS. N-type substrate, the name will be PMOS. P-channel MOSFET. What is the meaning of PMOS? P-channel MOSFET. So here I can write down the full name, N-channel MOSFET. So I can call it NMOS. N-channel MOSFET is NMOS. What is the meaning of N here? N means electrons. Electron flow would be there. Here holes flow would be there. So even though this is N substrate would make PMOS. P substrate would make NMOS. Can you remember it? Surely sir, I will be able to remember. P substrate would make NMOS and N substrate would make PMOS. Opposite. Okay. What else I can talk here? Now we need to give it some supply, right? Some supply we will have to give. Like if I want the current flow, how these electrons will travel, we need to make these electrons travel. So we will have to give some supply, right? So when we studied MOSFET, we always kept a body at ground. So here also body will be at ground, but we will study one concept that is known as body effect. There this ground will be gone. Now I need to apply, let's just say at gate I need to apply some potential. Let's just say at gate I am applying 4 volt. So this 4 volt I am applying with respect to something, no? 4 volt with respect to ground, right? With respect to something I need to apply. Drain, let's just say I need to apply 3 volt. So with respect to something I am applying it. So we will apply all the voltage with respect to source. So I will keep source as ground in both of the scenario. But it is not always necessary. What I mean to say is that, sir, at gate I want 4 volt. And let's just say my source is at 1 volt. Let's just say source is not at ground, it is at 1 volt. So at gate what I will apply? 5 volt. Basically source is taking as a reference, which is at ground. If I am saying that at gate I am applying 4 volt with respect to source, that means gate is at 4 volt, source is at 0. If I say at gate I am applying 5 volt with respect to source, so source is at 1 volt and gate is at 5 volt. Basically potential difference I want to maintain 4 volt. So if this guy is at 1 volt, this will be at 4 volt. So always I will not write down gate potential, I will actually write down gate to source potential. So all the analysis you will do with respect to source. Is that clear to you? So source will always be grounded. Source will always be grounded, and until we discuss the body effect, body will also be grounded. Is that clear to you? So source and body will always kept grounded until we discuss the body effect. We will see if body is at positive or negative potential, what will happen, that we will also see. But as of now, source and body both will be grounded. Is that clear to you? So are you able to understand this structure? This channel length is shown by L. What is this L? L is the channel length. That means this much of gap. This gap is L. Or better I can show here. Okay. I can show the gap here. This is known as channel length. Now this is the 2D structure we are seeing, right? But it will be there in 3D. What I mean to say is that this will be a 3D structure, no? It would be backward as well. It will be a 3D structure. So this structure would be there in 3D. So the structure would be somewhat like this. So this is your channel length L. This is your channel width W. Channel width. Are you able to understand this point? This is your channel width. So this structure we have already seen, metal oxide semiconductor, then this is N plus region, this is source they are calling, this is drain they are calling, this is your channel region, this is your p-type substrate, here it is your p-type substrate, this is your body, we either call it body or we can call it substrate as well, right? You call it p substrate or p body, whatever the name you want to give, N substrate or N body, this terminal is known as body. Now someone would be having the doubt that, sir, why they are putting metal here? Why this metal? So look, whenever you make any contact, in our IC, in our chip, how will you make the contact? Let's just say there is one circuitry here, another circuitry is here. You need to join both of the circuitry. So you will make the contact with respect to a wire only, no? This has to be a wire. And wire has to be metallic. Wire has to be conductive, no? That's why there will be a contact. Otherwise, there will not be any contact. So let's just say this is the drain of one MOSFET. Now another MOSFET is there, which is having its source here. Now I need to connect this drain to source. This is the source of some other MOSFET. This is the drain of this MOSFET. So I need to connect both of them. So always I will connect with the metallic wire only. So there has to be a metal contact. That's why this metal is there. There is no use of this metal when we understand the physics. That's why here I did not make the metal. but actually metal will be there. Here also metal will be there to make the connections. Is that clear? To make the connections, these metals will be there. And from here, if anyone can think why this was N plus, why this was N plus, why it was not only N, like why I am doing strong doping here, why I am doing strong doping here. Can anyone think of it? Why I could have simply made it N? No, I could have simply made it N. Why N plus? Because I know that over this N plus there will be a metal, right? And metal is having good enough charge carriers. N is having more charge carriers, or N plus is having more charge carriers. Like which guy is more towards metal? If I say out of these two you choose one to be metal, whom will you say that sir this is metal? This guy will be metal, no? Because this is having more carriers. So that means N plus and metal are closer to each other than and metal. These guys are far away, these guys are closer to each other. If two guys are closer to each other, that means there will be lesser built-in. That means there will be lesser junction. If it was N plus and N plus, there was no junction, right? There wouldn't have been any junction. There wouldn't have been any electric field. So this is the needless electric field which we are getting because of the junction, because we connected two devices. So here also, when I am connecting my N plus to metal, then the junction will be very small. In our whole electronics, I will always try to reduce the junctions. To reduce the junction potential, what I have done, I have doped it higher. Higher doping means, why higher doping? Because if this doping is higher, then I surely know that I will be connecting it to some other guys. That means I will have to make metallic contact. Metal will have more carriers. So I need to make it look like a metal only. More carriers, lesser junction would be there. So to reduce the junction, I made it N plus. Somewhere you can write it down. Okay, I am giving you this gap. Somewhere you can write it down. These are some good interview question. So I am not going to explain it again. Here only I have explained why this is N plus. N plus metal. N plus metal. Less junction. N metal. More junction. You will be able to understand the meaning. Understandable? So that's why we are doing the doping higher here. Why, like in the interview they can ask why it is N plus, why not N? So you will be able to tell that sir, eventually metallic contact would be there. To reduce the metal semiconductor junction, we have done more doping here, and here lesser doping would create more junction. To avoid the needless junctions, we are doing the doping here. Well and good. Okay, fine. Let's try understanding the working. So first let's see the equilibrium. I told you always source and body will be at 0. As of now, we are keeping gate at 0 as well and drain at 0 as well. Everything is at 0. That means this is the equilibrium. So now I am going to draw source, channel and drain. Source, channel, drain, energy band diagram. So your source is N plus. Your channel is, as of now your channel is P type, and your drain is N plus. So this is the scenario. So N plus P N plus, energy band diagram. N plus P N plus, source, channel, drain. At the equilibrium, equilibrium means no current at all. What will happen? These guys will be inclining. Like Fermi level will become at one place only. Fermi level will become at one place only. Drift diffusion, perfectly cancelling out each other, zero current. Physically, if you need to see, sir, this is N plus side and this is P side. This is N plus, this is P. So, can you see a diode here? Sir, this is drain and this is P substrate. Can you see another diode here? N plus P, N plus P. Two diodes are there. Source, body diode, drain, body diode. Drain to body there is a diode, source to body there is a diode. Body is connected to ground. That means this is grounded. This is grounded. Is that understandable to you? Source, body. Source is N plus. Body is P substrate. N plus can be connected like this. And body is your P type. So that's why this kind of diode would be there. I told you how your PN would look like. PN. This is how I will show it. So this is how I have shown it. N plus NP. This is how I can show it. Say yes or no. Body is at ground, so I can show it ground. Body is at ground, I can show it ground. Drain is at ground. As of now, drain is at ground. Yes, sir. As of now, this is also at ground. Yes, sir. That means there is no bias here, no bias here, no bias at all. Perfectly current is zero. Drift diffusion cancelling out each other. Like there will be N plus P junction, there will be N plus P junction. Electrons will say that, sir, I will try to diffuse. These electrons will say that I will try to diffuse. But there will be electric field. Electric field will be saying go back. Electric field will be saying, what will be the direction of electric field? This will be the direction of electric field. What will be the direction of electric field here? This will be the direction of electric field. These are your built-in electric field. Built-in electric field. What electron said? I will try to diffuse. What electron said here? I will try to diffuse. But this electric field said go back. Electric field said go back. Drift diffusion, everything perfectly cancelling out each other. No current. Now I want some current to flow. So what will be the first thing that will be clicking to you? I have two nodes, gate and drain. At gate I can apply some potential, at drain I can apply some potential. So first what I thought of applying some positive potential at gate. Sir, why positive click to you? Why not negative? If you apply negative, then what will happen? At drain, if I apply negative potential, what will happen? Sir, this source will be at 0. At drain you are applying negative potential, let's say you are applying minus 2 volt. That means you are setting up the electric field in this direction. 0 is more positive than this minus 2 volt. That means you are setting up the electric field in this direction. If electric field is set up in this direction, then where the electrons will travel? Electrons will travel in this direction. But what do you want? You want electrons to come out of the source. Say yes or no? How did we start? This is how we start. From the source, electrons should come out and flow through the drain. From the source, electrons should come out and flow through the drain. So if I am saying that this is my source and this is my drain, so if I apply negative here, then electric field I have set up in this direction. In this direction I have set up the electric field. So how the electron will travel? In this direction electron will travel. So from drain electrons will go out and get into the source. This is not I want. This is not something that I want. What do I want? I want electrons should come out of the source and get into the drain. So what I have done? I have applied drain to be positive. Let's just say I have applied some 2 volt. Now let's see what is happening. So what do you feel? Sir, you have applied 2 volt. Then you feel that here there is 2 volt and here there is 0. That means you have set up a horizontal electric field in this direction. I have set up a horizontal electric field in this direction. If electric field is set up in this direction, then electrons will go out from here and they will start traveling. This is what you are feeling, and current should flow. But let's see deeply. Okay, put your full concentration, because at 10 out of 10 places it is taught wrong. That if your VDS is some potential and gate is at 0, why current will not flow? At 10 out of 10 places it is taught wrong. So let me give you the perfect explanation. Okay, so let's see that. So what you have done, you have applied VDS to be positive. Positive you have applied here. So what you are actually doing? Let's talk about this diode. Sir, here I have applied positive and this is at 0. Are you doing anything to the source? This was your source and no? This was your source and this was your body. This was your drain and this was your body. Sir, body is at 0, body is at 0, body is at 0, body is at 0. Source grounded. This body was grounded. Drain is at positive. So basically with this barrier, with this particular barrier, you are not doing anything. This barrier remains as it is. You have applied a reverse bias on this particular barrier. N is connected to positive, P is connected to ground. That means you have applied a reverse bias here. But this remains unchanged. Say yes or no? Under equilibrium also this was the condition. Under that, when you applied VDS, then also this is the condition. This remains unchanged, but this barrier has increased. So surely, sir, this barrier has increased. This barrier has increased. There is no doubt about it. But this barrier remains as it is. So here I will write down unchanged. But this has increased. Now what may happen? Sir, this was your P P, right? So some drift can take place here. Some drift can take place here, but electrons are not even getting out of the source. Are you able to understand this point? What was my prime target? Prime target was this much, that sir, electrons should get out of the source and then electrons should get into the drain, which is not happening at all. Electrons are not even getting out of here because this remains unchanged. No, previously when this was the scenario, drift and diffusion was perfectly cancelling out each other. There was no flow. Here also again there will be no flow. Surely here there can be some drift. I don't care about that drift because this was not my target. If I wanted to achieve this particular thing only, then I could have simply achieved it using PN junction reverse biased. Say yes or no. This particular thing was already achieved. So some minority carrier drift will be there, but I don't care about that. Minority carrier of electrons will be drifting here. This is your P side, no? Yeah. So minority carrier electron will be drifting here, holes will be drifting here. I don't care about these drift. I am getting very less drain current. It is known as drain current. What is the meaning of drain current? The current which is flowing through the drain. Our target would be to determine this current. This is our drain current. Look, electrons will be flowing in this direction, no? Electrons will be flowing in this direction. So drain current would be opposite. So I am showing the sign here. Electrons will get out of here and flow in this direction. So current would be in this direction. So drain current would be very low, or you can say, sir, current would be nearly zero. In reverse bias, the current is actually very low. So it's like this condition only. I explained this condition. Where I explained it, I told you this thing that, sir, you applied only this reverse bias. You are not doing anything here. Then what will happen? This IC would be simply a reverse bias current, which will be actually very low. Do I care about this current? Absolutely not. The IC current would be nearly zero only. Say yes or no. Understandable? So here what do you see? That, sir, if I apply VDS to be 2 volt or whatever the potential that I am applying, I am surely putting up some horizontal electric field, but this electric field is not enough for the electrons to get out of here. What kind of explanation I have seen? That electrons, even if this electric field is making sure that these electrons are getting out of here, then what will happen? Here this is P type, right? So in P types there will be a lot of holes. So electrons will be recombined with those holes. Absolutely baseless explanation. And the same explanation I have given in analog electronics. But that explanation is wrong. From my side as well it was wrong. From other side as well it was wrong. But in EDC you will get the correct explanation. In analog electronics I cannot explain by the Venn diagrams, right? So there I will have to say that electrons will get out and it will recombine with the holes. But that is absolutely baseless. The actual explanation is that, sir, you have forward biased, you have reverse biased this diode. Surely you have increased this barrier. This barrier has been increased, but you are not doing anything with this barrier. This barrier remains as it is. That means there will not be any flow. If there is no flow here, that means here whatever the current that you are getting, that is the reverse bias current, which is actually very low. And if you want this current only, then you could have fulfilled your purpose with this PN junction only. Why you need to make this MOSFET? Now, what do you think what we should do? So some guy would be thinking that, sir, I have increased this one, right? And I have studied BJT. In BJT, what we used to do, that, sir, we used to reduce this barrier. How we used to reduce it? By applying some forward bias here. So, sir, now our target is to reduce this barrier, right? We need to reduce this barrier because this barrier was unchanged. We need to reduce this barrier. How we can reduce this barrier? Sir, this is source. And sir, this is body. So, sir, what do? We forward bias source and body. So, someone would say that, sir, we need to forward bias it. So, source you are taking as a reference. So, at the body you apply negative. So, sir, it will be forward biased. And then, sir, this barrier would be reduced and current would flow. Yeah, it will flow. Surely it will flow. But then why did you make MOSFET? You could have achieved this particular thing using BJT only, no? Why you made MOSFET? What you are saying, sir, we need to reduce this barrier. Sir, problem is this particular barrier which is not being reduced in this scenario. When I applied VDS, that means I have applied a horizontal electric field. That means this guy is under reverse bias, but this is remaining unchanged. This barrier remains unchanged. I need to reduce it. What I can do? Sir, I can make it forward bias. So sir, what you do? I need to make it forward bias. No, sorry guys. I need to make it forward bias. So what I need to do? Sir, body you should connect at positive. This is at 0. Source you are taking as a reference. So sir, you keep this as 0 only, but you connect your body at positive. So this potential you make positive. So sir, it will be forward biased. So sir, since it is forward biased, then what will happen? This barrier will be reduced. If this barrier will be reduced, then there will be some flow and there will be high electric field as well. Current would flow. That means you are actually doing nothing new. You are already doing BJT only. So why you made MOSFET? Why you made this gate? Why you made this metal oxide? What is the use of this metal oxide here? If you want this operation only, you could have done this particular operation using BJT only. Why you are making MOSFET? So you can surely use your MOSFET as a BJT, where this guy will work as a emitter, this guy will work as a collector, and this guy will be working as a base. Are you able to understand this point? If I don't even want to use this guy, then just keep it at 0 potential. Keep the body negative. Sorry, keep the body positive. This will be forward bias. This will be reverse bias. Your job is done. But you are following the operation of BJT only. No, why did you make the MOSFET? I want to use the MOSFET. I want to use the gate terminal. I want to control the current using this guy only. This gate is very important for me. This is very important for me. Why it is important for me? Because I want to control the current using this gate. I want to control the current using this gate. And can this gate do anything? Surely it can do anything. So at the body, until I say I will keep it at 0 only, I will not do this particular thing. Now, so I want to reduce this barrier, but I will not reduce it using this forward bias. First thing is this clear. Is that clear to you? That barrier I want to reduce, but I am not going to reduce it using this particular strategy. Is that clear to you? Say yes or no. Okay. You study 20 books, you are not going to find out this explanation. Okay. Right. So what do you think what I should do now? I will go to gate and I will ask him, can you do anything? I am asking to gate, can you do anything? Gate will say, yes, I can do something. Gate will say that if you apply my potential, let's remove this 2 volt. Gate is saying that if you apply my potential greater than VT, if you apply VGS greater than VT, if you apply my potential greater than VT, then sir, near my surface, this P type I can convert it to N type. This is what gate will say. That if you give me sufficiently large positive voltage, this is your metal oxide semiconductor, this is P substrate. If I apply positive voltage, what will happen? Holes will be repelled, electrons will be increasing. So near the surface, you will get an inversion layer of electrons. So what you will get? You will get an N-type layer. So gate will say that if you apply VGS greater than VT, then I can make an N-type layer here. So sir, previously you were seeing N plus P. Here your junction was N plus P. But now the junction would become N plus N. And I have told you one thing, that N plus P and N plus N, if you compare, then N plus N will have a lesser barrier than N plus P. There you go, you have reduced the barrier. Okay, using the help of a gate potential said that if you apply my gate potential greater than VT, then I can make it N type. Then your junction would become near the surface. We are talking about near the surface only. Okay, we will talk about near the surface only. As of now, sir, it was N plus and P type near the surface. Then this was the band diagram you were getting. But now, sir, I have made the surface to be N plus N. And if N plus N surface is there, if N plus N junction is there, that will have a lesser barrier than N plus P junction. Have we seen it? Surely we have seen it. N plus P junction would be having more barrier than N plus N. That means if I made this particular junction, sorry, if I apply VGS greater than VT, then here this layer, a very thin layer of N type I will get, and I will get here I will get N plus N junction. This would become your N plus N junction. And if it is becoming N plus N junction, then this barrier will be reduced. Already this barrier has been increased, this barrier has reduced, then what will happen? Electrons will diffuse from here to here. Electrons will be diffusing and then they will be feeling a very high force. This will be the very high force. Since they are diffused here, what they will feel? A very high force they will feel, and in this direction they will travel, and we will get a good amount of current. Using the gate voltage, we have controlled our current, and this was our target. There you go. We did nothing with the source and body. So did you understand how we moved from BJT to MOSFET? What is the difference between BJT and MOSFET? Will you be able to tell the actual difference? You will say, sir, if I want to use MOSFET as a BJT, I can directly see NPN. Surely it can work. Although it will not be a good BJT because this channel length will be larger. Okay. Like in BJT, I did not explain that why this length should be lower. This length is actually very low. P plus region, this is very low. Along with that doping, this doping is actually very high. Why this is higher than this one? All these are discrete points. All these are like separate points which we are not going to discuss as of now. But the point is like you are kind of getting BJT structure here, right? So first I saw that if I give only positive supply here, this would become a reverse bias. And if it is becoming a reverse bias, so some reverse bias current I am getting here. But I don't want that current. Right? If I wanted this reverse bias current only, I could have simply used PN junction. So what do I actually want? I actually want, or you can say here current is already zero. What do I actually want? I want that electron should be coming out of the source and it will be reaching to the drain. Then the second idea that came to my mind was, sir, why not keep body as positive? If I keep body as positive, what will happen? This will become forward bias. This barrier will be reduced. If this barrier is reduced, then electrons will be diffusing and then they will be drifted. Electrons will diffuse and then they will be drifted. But if you want to use it in this manner only, then better use BJT. What do I want? I want gate to control the current flow. Then I went to the gate. I asked him, can you control the current flow? Gate said that, yes sir, I can control the current flow. Then I asked him, how will you control? Then gate said that, sir, if you apply my potential sufficiently larger than VT, then I will give you an inversion layer. That means, sir, this particular region I will make N type for you. So previously you were having N plus and P junction. There your barrier was large, but now your N plus and N junction will have a reduced barrier. So sir, controlling this gate voltage, I have reduced the barrier. Now the electrons can diffuse and then they can be drifted as well. Say yes or no. Understandable? Okay. So for VGS greater than VT, we are not drawing the band diagram as of now. In the third lecture, we will draw it. As of now, we are not drawing the band diagram. Okay. In third or fourth lecture, we are going to draw it. But what did you understand till this point? That this is the setup. This is the setup we are having. That you apply your VGS greater than VT. This is at ground. This is at ground. If you apply VGS greater than VT, what you will get? In this channel length L, you will get an inversion layer of N type inversion layer. Right? And here you are having VDS as well. What this VDS will do? This VDS will give you high electric field in this direction, high electric field in this direction. Because of this electric field, what will happen? The electrons can feel the force and they can travel. So this is doing the job of giving the force to the electrons. Electrons will travel, and here this is the depletion region that we are having. Sorry, not depletion region. Sorry guys. Inversion layer that we are having, and here in this inversion layer as well, there are a lot of electrons. So in the force of this particular electric field, these electrons can also travel. In the force of this particular electric field, these electrons can also travel. So you will get a good amount of current because of these inversion charges as well, because of the electrons which are coming from the source as well. All good. Now when we studied MOSFET, what did we write down? That Qin is equals to COX Vg minus Vt. So there only gate voltage was controlling the inversion charge. This we wrote down for Vg greater than Vt. That if you have applied Vg greater than Vt, after that inversion charge will start coming into action. Right? So there only controlling potential was gate voltage, because there we were studying only this much of scenario. But now drain voltage will also control these inversion charges. How they will control, we will see it. Because a lot of people would be having the doubt that, sir, if you are applying drain potential here, let's just say you have applied 2 volt here. Now this 2 volt will be distributed among this particular MOSFET, no? Like here you are having 2 volt, then here you may have 1 volt, here you may have 0.5 volt, and here you will be having 0 volt. So you have applied, sir, you have applied 2 volt between these two guys. Between source and drain you have applied 2 volt. So this 2 volt will be distributed here, no? This will be the doubt you are having. So sir, this inversion layer will be having an effect of VGS as well, it will be having an effect of VDS as well. Surely it will have an effect of VDS, but that effect we are going to see later on. Is that clear to you? As of now, you just think that this VDS is actually low. This VDS is low, that means this VDS is putting no effect on the inversion charge. Is that clear to you? So all these lines we have put. If VGS is less than VT, no current would flow. VGS greater than VT and VDS is greater than 0, then current would flow and inversion layer is also framed. Right? Now at a low value of VDS, or you can say when VDS is, like this is not a hard and fast value, this is not a certain value, just an approximate value I have taken. When VDS is between 50 millivolt to 100 millivolt, or 0.05 volt to 0.1 volt, and VGS is greater than VT. That means inversion layer has been framed, but now your inversion layer is only depending on VGS. It is not depending on VDS. Okay. So what I am saying here, that your inversion charge is not a function of VDS. This is something that I am saying here. Is that clear to you? Okay. So basically I am saying that VGS is greater than VT. So there is a fixed VGS that you are having. If VGS is fixed, VT will be a certain value, CUX will also be fixed. What does that mean? That means inversion charge is also fixed. At a fixed VGS, you will have a fixed inversion charge. This is what we are saying. But when we study our MOSFET, we write down inversion charge in this manner. Q in equals to CUX VGS minus VT multiply with WL. Because our COX is capacitance per unit area. This was your MOS cap. Okay. In MOS cap, COX was different. Here COX will be different. So I will not put COX dash. Ideally, if I am saying this is my COX, this I should put as COX dash. But later on, as of now, let's put it COX dash. So COX dash is nothing but capacitance per unit area. So what will be the area? So area will be W multiply with L. This will be the area of your oxide layer. So what will be the area? Sir, here the area would be, this will be the area. Area would be W into L. So cross section area is W into L. So in your whole MOSFET, even in the examination as well, your capacitance would always be mentioned in farad per centimeter square. So here I have multiplied with the area. Okay. So from now onwards in MOSFET, what I will be writing down in MOSFET, I will be writing down your Q inversion as COX into VGS minus VT WL. This is how I will be writing it down, and by default you need to consider that this is COX here is having a unit of farad per centimeter square. By default you will have to consider it. So farad per centimeter square multiply with W into L, that will be centimeter square. So centimeter square and centimeter square will get cancelled out. So this will become farad. Farad multiply with the voltage, what you will get? Charge. Clear? Understandable? So here I will not show COX dash, I will show COX only. Okay. So that is the that is something you need to take care. This was the scenario in our MOS cap. In MOS cap, I used to show by COX dash. If I used to calculate capacitance per unit area, I used to show it by COX dash. But here I will show by COX only. So this COX is capacitance per unit area. Is that clear? Now low value of VDS is there, that means it is Q inversion charge is not a function of VDS. So can you find out the current? Can you find out the current? Yes sir. Current means drain current. What will happen? Electrons will be traveling, because of this electric field, electrons will be traveling in this direction. And if electrons are traveling in this direction, then there will be a drain current that will be flowing. Electrons are traveling in this direction, so drain current will be flowing in this direction. So I am finding out the expression of drain current. I am finding out the expression of a drain current for low value of VDS. Very, very important. For low value of VDS, I am finding out the expression of a drain current. How low, that we will see. Okay. For low value of VDS, we are finding out the expression of drain current. So what will be your current? So current will simply be charge divided by the time. Now what will be this time, sir? This time would be distance. What is the formula of time? How q in by tau I have written now? Current equals to charge divided by time, right? Say yes or no. I equals to dq by dt, charge divided by time. Now what will be the time? Time would simply be, what is the formula of time? Time is distance upon speed, right? Distance upon speed. So length upon the drift velocity of electron. Channel length, L is the channel length, Vd is the drift velocity of electron, N is the channel length, and Vd is the drift velocity of electron. Right? Basically, if some electron is getting out of the source, then it will cover the distance of L only, no? Like just as it covers the distance of L, drain is available. This is what we will assume, that it needs to start from here and it needs to reach here. So it needs to cover a distance of L, and what will be its drift velocity? That would be Vd. And Vd can be written as mu E, applied electric field, and E could be written as Vds by L, because across the length L, you are applying Vds potential. Someone would be saying that, sir, till this particular length we are applying Vds potential, but you have to assume that Vds is completely applied across the channel only. Why is that so? Because, sir, this is N plus, and your channel is N. This is your N plus, and this is your channel in length L. This particular channel is N region only. So let me show it somewhat like this, that this is your N region. This is your channel, which is your N region. And you are applying the potential here, which is Vds. So just answer me one thing, where the most of the potential would drop? N plus, lesser resistance. More charge carriers, lesser conductivity. More conductivity. Sorry, less charge carriers, less conductivity, that means more resistance. And here, lesser resistance. So most of the potential would be dropping here only. So you will have to assume that all the potential that you have applied, Vds, that will be dropped across this length only. So electric field can be written as Vds by L, right? So your tau would be simply L mu Vds by L. So this would become L square. This would be your tau. So what will be your ID? ID is, and here you are talking about electrons, so mu n I can put, right? Because we are talking about the electrons. Electrons will be traveling, no? So mu n I can put here. So what I can put? What is our inversion charge? Inversion charge is COX Vgs minus Vt into W into L. COX Vgs minus Vt W into L. Downward there will be L square, and here tau. Just I am putting this value of tau. L square mu n Vds. Mu n Vds will go upward. Mu n Vds will go upward. So this and this will get cancelled out. What you are getting? ID equals to mu n COX W by L Vgs minus Vt into Vds. There you go. So what is the relation between ID and Vds? If I draw the diagram of ID versus Vds, what will happen? For low value of Vds, it will increase linear relation between ID and Vds. But don't forget that Vds is low. Vds is low means Vds is not affecting the inversion charge. So for low Vds, so for low value of Vds, you are getting a linear relation like this. Till the low value of Vds we have seen. ID versus Vds plot we have seen. Mu n COX W by L Vgs minus Vt into Vds. This equation you don't need to remember, but derivation you have seen that this is how we are deriving the equation. This expression you don't need to remember. Which expression you need to remember, that I will tell you. Okay. This expression you don't need to remember, but derivation is clear that if you increase your Vds value, let's just say low value we are saying, no. So let's just say my Vds was some 10 millivolt. So 10 millivolt potential, this 10 millivolt potential was dropping some electric field. In the presence of this electric field, electrons were feeling some force, so they were traveling. If you increase the potential from 10 millivolt to if you go to 50 millivolt, then what will happen? More electric field will be there. Electric field will increase. That means electron will feel the more force. That means they will be attracted with more force. Their velocity will increase. Their velocity increases, then their velocity. What is the current? Current is NQ mu E. More electric field, that means more current. And here, who is the major part? Major part is drift, right? Because of the drift, electrons are flowing. Eventually, this electric field is pulling now. Are you able to understand this point? When I talk about VDS, when I am talking about VDS, that means VDS, what VDS has done? VDS has increased this barrier. So, if this barrier has increased, that means here drift has increased. So, when I talk about this ID current is mainly because of the drift of the electrons. Surely, from here to here there was diffusion, no doubt about it. Surely there was diffusion, but eventually the electrons are pulled by this particular force. So, current is drift dominant here, right? So, this VDS, what this VDS is doing, if you are increasing more VDS, that means more electric field will be there. That means their drift velocity will increase. This is your drift velocity. If drift velocity increases, then your drift current also increases. So, this was your drift current. This is the expression of your drift current. So, drift current also increases, right? So, this was for the low VDS we have studied. This kind of linear graph we are getting, and this is known as linear region. What it is known as? Linear region. So, this is the linear region of operation. This is known as linear region. Now, we will see that if we increase the VDS, then what will happen? If your VDS is significant, then what will happen? But I need to take a break because it's been roughly around 100 minutes since I am talking. Okay. So, surely I need to take some break. But now your VDS is significant. If VDS is significant, then what it will do? It will make some impact on the inversion charge. And if it is making some impact on the inversion charge, then inversion charge would also become a function of VDS. Then what all things will happen, how the waveform would go, that we are going to see. Okay. So, let me take a break and then I will come back. Yeah, welcome back guys. So, we were studying about MOSFETs. So, we have seen this characteristics for low VDS value. And when we are drawing the characteristics, we are keeping VGS constant, right? This has been drawn for a particular VGS. Someone would be saying that, sir, your ID is depending on VGS as well, it is depending on VDS as well. You are drawing ID versus VDS for fixed VGS. Fixed VGS. Now, VGS is fixed, VT is already a certain value, right? Threshold voltage will be a certain value. Mu n fixed, CUX fixed, W by L that is also fixed, right? So, everything is fixed, only variation is VDS. So, if VDS increases, ID increases linearly, right? Now, we are going to see the effect of VDS when it is significant. So, basically this inversion layer has been framed. What does that mean? That means we have already applied gate to source voltage to be greater than VT. Like this is our gate. So, we have already applied VGS greater than VT. This condition we have already done. Now, VGS is fixed. We need to see the variation with respect to VDS. So, what I am saying that let's just say VT was 3 volt. Let's just say VT was 3 volt. VT was 3 volt. So, I have applied VGS equals to 4 volt. Now, I am keeping it fixed. This is fixed. Fixed potential is there. Now, because of this VGS, this inversion layer has been framed, right? When there was no effect of VDS, no effect of VDS, then your inversion layer was Qin was CUX VGS minus VT, right? When VDS was low, right? This is the formula of Q inversion we have put. But now the effect of VDS would also come into action. How this VDS would be affecting, that we need to see. As of now, we will not talk about VGS at all. We will only talk about VDS. Now you know that most of the potential of VDS would be dropped across this inversion charge only, right? Across this channel only. So what kind of channel it is? Sir, it is N channel. Just tell me one thing. When you apply VGS greater than VT, surely there will be an inversion layer. But along with that, you will get a depletion layer as well. I hope you did not forget this depletion layer. There will be a depletion layer as well. So two things are there. Depletion layer is also present, and along with the depletion layer, inversion layer is also there. So we cannot forget depletion layer. So there is a depletion layer present, there is an inversion layer present. Now whatever the VDS that I apply, this is sufficient enough. This is good amount of significant VDS we are applying. So that VDS would be dropped across this particular region only. Here it will be dropped. Now let's just say this channel is having a resistance of 4 ohm. Or let's just say it is having a resistance of 3R. Okay, this is your R channel. This is your channel resistance. Here you are having VDS potential. At this end you are having VDS potential, and here you are having ground. This is the scenario, right? Now what I am doing, I am breaking this 3R in this manner. R, R and R. In this manner I have broken it. And I am assuming that this VDS is 3 volt. This is 3 volt. So now how the potential will be divided? So 2 volt, 1 volt and then 0 volt. What is your channel? This is my channel. This is my channel. Sir, my channel is N type and my substrate is P type. Channel is N type, substrate is P type. So kind of I can make diode like this. Channel is N type, substrate is P type. Substrate is grounded. Again, channel is N type, substrate is P type. Basically, I am making a diode somewhat like this. That this is your channel which is N type. I am ignoring the depletion region. Channel is N type and substrate is P type. So there is a diode present. Channel substrate diode is there. Channel substrate diode is there. Channel substrate diode is present. So yes or no? Here also this is the this is the end of channel, no? At the end of the channel as well there is a diode present. Now because of this positive VDS, all of these diodes are reverse biased. All of them are reverse biased. All of them are reverse biased. How they are reverse biased? Sir, this is at 0, this is at 3. Sir, this is at 0, this is at 2. This is at 0, this is at 1. N side is at positive potential, P side is at 0. All of them are reverse biased. But who is getting the most reverse biased? Sir, this is getting the most reverse bias. Most reverse biased. And he is getting the least reverse bias or 0 reverse bias. You can see that 0, 0. So 0 reverse bias is there, or I can say that least reverse bias. So as you are moving from drain to source, listen to the statement very carefully. As you are moving from drain to source, your reverse bias is getting decreased. That means at the drain side you are having the maximum reverse bias. At the drain side you are having the maximum reverse bias because of this VDS potential. If you are having the maximum reverse bias, that means depletion width will also be maximum. Would also be maximum. And if depletion width is more, that means depletion charge will also be more. Now you know what is your VGS. VGS is fixed. This is a fixed VGS you are applying. VGS is equals to, sir, VOX plus the surface potential. We will not talk about the surface potential, but I know that, sir, what is my VOX? Sir, it is Q in plus Q depletion divided by COX plus 2 phi f is there. This is VGS. You know that, sir, this is fixed. It is neither increasing nor decreasing. This is fixed. Let's not talk about this guy. COX will be fixed only. You can see that, sir, depletion width is maximum. That means depletion width is increasing. What does that mean? Inversion charge has to decrease. Basically, you need to keep VGS fixed. Let's just say 2 phi f is also fixed. Although it will increase. Why it will increase? Because depletion width has increased. If depletion width increases, that means the potential across the depletion width will also increase, no? But as of now, let's not talk about it. I'm just saying that depletion charge is increasing, right? Because depletion width is increasing. Here, you are applying a reverse bias. In reverse bias, what will happen? Depletion width increases. If depletion width increases, then depletion charge increases. If depletion charge increases, then here your inversion charge is getting lesser. Because if this guy is increasing, then VGS will also increase. But what you need to do? You need to make VGS fixed. That means inversion charge has to decrease. So that means at the drain side, inversion charge is getting lesser. At the drain side, inversion charge is getting lesser. So let's draw the diagram. We will read this theory later on. But this was your channel at low VDS, when there was no effect of VDS. Let's just say VDS was some 10 millivolt. So 10 millivolt, there was very low reverse bias. So in the in the presence of very low reverse bias, they were very low reverse bias, so Q depletion was not changing significantly. But now Q depletion is changing significantly. So this was your channel first. Channel was constant everywhere. It was uniform everywhere. But now what will be your channel? How will your channel look like? So sir, at the source side, this is my source side. And this is my drain side. Sir, at the source side, nothing is happening. This is under very low reverse bias. If it is under very low reverse bias, then sir, depletion region remains the same. If depletion region remains the same, that means inversion charge remains the same. But as you are moving towards drain region, then depletion charge is increasing and inversion charge is decreasing. So this kind of channel you will be getting. Look, here you are having N plus region. Here also you are having N plus region, which we are not drawing. This is the source side, this is the drain side. But as you are moving towards that drain, then inversion charge is getting lesser. Here there is a lot of inversion charge. So now inversion charge has actually become a function of x. What do you mean by function of x? If I say this is my x equals to 0 and this is my x equals to L. So now your inversion charge has become a function of x. And who is the region behind it? The applied VDS potential. Applied VDS potential is the region behind it. Is that understandable to you? From x equals to 0 to x equals to L, your inversion charge is getting less. Or you can say depletion charge is increasing. Here depletion charge will start from here, right? But slowly as you move forward, you can see more depletion charge, more and more depletion charge, right? Here more depletion charge, more and more depletion charge, right? More and more depletion charge is increasing. Now here what you are having? N plus, right? N plus you are having here. This is the N plus we are having, right? So in N plus, this will be the scenario, right? Like there will be a depletion region between N plus and P as well. So this will be the scenario in N plus. That means there will be an electric field in this direction. Say yes or no, right? So there is an electric field in this direction. Previously as well, there was an electric field. Because of this VDS, when VDS was low, there was also an electric field. But now what is the scenario? Now this electric field has become a bit stronger. Inversion charge is getting lesser. Surely your inversion charge is getting lesser. So people would be thinking that, sir, inversion charge is getting lesser, then current should get lesser. Yes, current would get lesser. But along with that, because of higher depletion region, the electric field has become a bit stronger. That means current will increase only, but it will increase a bit slow. Why it is increasing a bit slow? Because inversion charge has become lesser. Why it is not very slow? It is not very slow. Why it is not very slow? Because electric field is also increasing. Two phenomena is happening. Electric field increases, inversion charge decreases. Inversion charge will say that I will make the current lesser. But electric field will say that inversion charge is lesser, but I will pull you with more force. Current will increase, but not very fastly. Previously, it was increasing linearly, but now it will increase in this manner. So this was your linear region. Now the region would become sublinear. Let's understand it with one more perspective. With one more perspective we can understand, but let's first read out the theory. Okay, let me give another perspective here. I can give another perspective here as well. So how can I show it? Previously your R channel was 3R, right? R channel we put as 3R, and we had a VDS potential. Like here we had a VDS potential. Here we had a VDS potential. Let's just say this VDS was 0.1 volt. Okay, this VDS was 0.1 volt, right? So here you had a VDS potential which was 0.1 volt. This is your R channel. This is your R channel. VDS was 0.1 volt. So what will be the current? Sir, ID current would be nothing but 0.1 by 3R. Now this scenario you are getting as at 0.2 volt. This has happened at 0.2 volt. So now let's talk about the R channel. Sir, in this R channel, this particular resistance was R. Then this was also R and this was also R. Here the resistance was R, R, R. But now, sir, here the resistance is R. But as I move further here, what do I see? That here the conductivity is lesser, you are having less charge carriers and you are having more depletion. That means conductivity has become even lesser. If conductivity has become even lesser, that means more resistance you are getting. So let's just say, sir, previously this particular part was R, but now, sir, the next part has become 2R and the next part has actually become 3R. So now, sir, this is my R channel. This is my R channel. Sir, this is my R channel now. Okay. Here 0.1 by 3R you are getting, here 0.3 by 6R we are getting. So let's just say this scenario has happened at 0.8 volt or 0.8 by 6R. If I need to compare, this is 3 times, right? 0.2 by 6R if I put, then it will not be good. 0.4 by 6R if I put. 0.4. Let's just say this is 0.4 volt. Again, I'm just explaining that current will surely increase, but it will not increase as fast as previous. Okay. Although intuitively also we have understood that what is the scenario, that sir, here inversion charge is getting less and electric field is getting stronger. Current will increase but not very fast. But let's understand with this scenario as well. Here what we are doing, here my VDS is 0.4 volt. Sir, VDS is 0.4 volt. So now what is the current we are getting? Point 0.4 by 6R. This is the current you are getting. How can you write down this current? Sir, this current is 0.2 by 6R. Right? This was your current here, 0.2 by 6R. Here the current has become double. This is your ID1, this is your ID2. So your ID2 is double of ID1. So current has become doubled, but voltage has become 4 times. This is your V1, this is your V2. So voltage became 4 times, right? But the current became 2 times only. If it was linear rise, then if voltage is becoming 4 times, then current would also become 4 times. But this is not a linear rise. Okay, just 1 second. I need to turn off the net. Yeah. So this is not a linear rise. If it was a linear rise, then this scenario would not take place. In the linear rise, if you are going from 0.05 volt to 0.05 volt to 0.1 volt. So there what was happening? Sir, my voltage was becoming, my V1 voltage was becoming twice of V0 voltage. So along with that, my current was also becoming twice. This was the scenario for low VDS because this particular thing was not changing. But here if this particular thing is changing, that means there this R channel was same. This was 3R. At 0.05 volt as well, R channel was 3R. And here as well, your R channel was 3R only. For low VDS, R channel was same, but now R channel has increased. If R channel increases, then current will decrease. But along with that, this potential is also increasing. Potential increasing means along with that, this electric field is also increasing. So what it will do, effectively your current will increase only, but not very fast. That means effectively first I saw the waveform as linear rise, but now the rise would be somewhat like this. Is that understandable to you? So this particular region was your linear region. And this particular region was your sublinear region. Okay, the complete theory has been written here. I am not going to read it for you. You can read it on your own and you will be able to understand every single line. Okay, now what we are going to do, we are going to further increase the reverse bias. Further increase the reverse bias, or you can say further we are going to increase the VDS value. Now VDS we are further increasing. Let's just say VDS we have made 0.8 volt. So at some point what will happen? At some point what will happen? Sir, here this is the scenario because source is not affected. Source side is not affected. But here, sir, it will keep on depleting, and who knows, from the drain end, your inversion charge has become 0. At the drain end, at this particular end, your inversion charge has become 0. That means the drain end is completely depleted of charge carriers. This drain end is completely depleted of charge carriers. Right? Now here you will be thinking that sir, current would be zero now because drain is completely depleted of charge carriers. What will happen is that sir, from the source, let's make the source side. Sir, this is my source side and sir, this is my drain side, which is N plus. So from the source, what will happen, sir? A lot of electrons will get out. It will travel through the channel, and then sir, it will travel through the channel, and sir, this is the drain side that we are having, and then it will get into this drain. But what will happen, sir? From here there are no charge carriers. So now the electrons will not be able to go ahead. This is what you are thinking. But along with the depletion, what is happening? If depletion width is more, that means electric field has become even more stronger. Although this R channel has increased, but potential has also increased, no? Because of that, depletion width has also increased. Because of that, electric field has become even more stronger. And if electric field has become even more stronger, then electron will be pulled with more force. So this particular point is known as pinch off. What is the meaning of pinch off? This channel is completely depleted of charge carriers from the drain end. Channel is completely depleted of charge carriers from the drain end. This particular point is known as pinch off. So here pinch off has occurred. So this theory would have been written here. If we keep on increasing the VDS, the reverse bias at the drain would become stronger at the drain side. At the drain side would become stronger. Because of this, the depletion region on the drain side would keep on increasing, and the channel near the drain keep on losing more and more electrons. That means it will keep on getting depleted of charge carriers. At a particular VDS, the depletion region on the drain side becomes so large that the entire drain end of the channel loses mobile charge carriers. In other words, the channel at the drain end becomes completely empty of electrons, or you can write down better word would be charge carriers. It is completely depleted of charge carriers. This point is called pinch off. Pinch off simply means that drain side of the channel has been pinched or cut off of its inversion charge. But here you might think that sir, current should be zero, but no, current would be there, but the current rise will not be much. Are you able to understand this point? Like once the pinch off has occurred, after that current will not be rising. So once pinch off has occurred, what will happen after that? So let's check that out. So first thing is that here at 0.8 volt, I am assuming that at 0.8 volt at drain and pinch off has occurred. At 0.8 volt at drain and pinch off has occurred. This is what I am assuming. Now what I am doing? I am increasing more VDS value. Now VDS I have put as 1 volt. So how will my channel look like? So let's check that out. At the source end there is no issue, sir. At the source end there is no issue. At the drain end, even at 1 volt you are getting the pinch off. Sorry, even at 0.8 volt you are getting the pinch off at drain end. So surely at 1 volt you are getting the pinch off. But what will happen? If here you are having 1 volt, then somewhere here you will be having 0.8 volt, no? Are you able to understand this point? This is the channel. This is our channel. This is our channel. Now I am saying that here I am applying 1 volt. So somewhere in the channel, this is 1 volt, this is 0 volt. Source is under 0 volt. This is 1 volt. So somewhere in the channel, at some point you will be having 0.8 volt. Why so? You have seen this distribution that I applied 3 volt here, 3 volt, 2 volt, 1 volt and then 0 volt. So somewhere in the channel, you will be having 0.8 volt. And now this 0.8 volt is more than enough to deplete the channel. That means if you are applying 1 volt, then somewhere in the channel you will be having 0.8 volt, and till that particular point your channel will be depleted. That means your depletion region would look somewhat like this. Sorry, your channel would look somewhat like this. This is your complete channel. This is your complete channel. And here you are having the N plus region. Here also you are having the N plus region. So this is the N plus region we are having. This is the N plus region we are having. At the drain end was completely depleted already here. You increased more value. So now what it will do? It will keep on increasing the reverse bias. Now this diode which was present here, or this diode which was present here, all these diodes are under very high reverse bias and they are being depleted. That means they are increasing their depletion width. So here more depletion width has increased. Now charge carriers are getting less. So you might feel like that, sir, if charge carriers are getting less, then I might feel that my current would go down. But actually electric field will keep on increasing. So once this pinch off has occurred, after that inversion charge is getting lesser, along with that electric field is getting increased. Inversion charge is getting lesser and electric field is getting increased. Now both will make sure that current saturates. So once this pinch off has occurred, after that the current will be saturated. Sir, first it rises linearly, then it was not able to rise linearly because significant VDS was there, which was which was reducing your inversion layer. So if it was reducing your inversion layer, but electric field was increasing, electric field increases, inversion layer decreases, then somewhat what was happening, some current is increasing but not linearly but a bit slowly. You have increased your reverse bias, sorry, you have increased your VDS such high that here it is completely depleted of charge carriers. Drain end is completely depleted of charge carriers. Okay, and this shape is known as tapered shape. Okay, what it is known as? It is known as tapered shape. So drain end is completely depleted of charge carriers. Now here what you might feel like that, sir, current should be 0, but no. Inversion charge would come, like whatever the charge that is flowing from here, that would come till this point, then it will feel a very high electric field and it will be swept away. So current would still be there, but the point is after this particular value, after the pinch off, no matter how much VDS you increase, inversion charge will keep on getting less and electric field will keep on getting more. So more electric field means more current, but less inversion charge means lesser current. So this is saying that I will decrease the current, and this is saying that I will increase the current. So eventually what will happen is that both combined effect, the current will saturate. So after this, the current will saturate in this manner. Whole theory has been written and this theory you can read. At the value of VDS where it is occurring, we will call it VD set. The value of VDS where, and VGS we are keeping fixed. Okay, this graph we are making keeping the VGS fixed. So VGS was fixed at a particular voltage which was 4 volt or whatever we assumed here, it was fixed. We are just increasing the VDS value. When we are increasing the VDS value, what is happening? Your channel is being depleted from the drain and it will keep on depleting, it will keep on depleting, and it will keep on reducing the speed of current. Like here the current was increasing in a very good manner, but now the current is slowly increasing, and after some point when the drain end is completely depleted of charge carriers, the current would saturate. After that the channel length will keep on reducing, but this high electric field and these charges would make sure that the current saturates. So current would saturate, and this point would be known as the value of VDS where the current saturates. Is VD set. Okay, so this value will be shown by VD set. Okay, or we should write down VDS set. Better would be VDS saturation. VDS set. This value will be shown by VDS saturation. Okay, for every MOSFET this value is fixed. How much is this value? We will find it out. Okay, this value would be equals to VGS minus VT. Okay, here I can write down VD set is actually equals to VGS minus VT. So this plot has been drawn for a fixed VGS, no? Right? For a fixed VGS, this plot has been drawn. So there will be a fixed value of VGS, there will be a fixed value of VT. If you have increased your, let's just say VGS was 3 volt and your threshold voltage was 1 volt. So if you have increased your VDS till 2 volt, after that no matter how much you increase it, from 2 volt to 3 volt you go, from 3 volt to 4 volt you go, from 4 volt to 5 volt you go, at all the voltages what you will find? That the current is same. At 2 volt, 3 volt, 4 volt, 5 volt, at all the voltages the current would be same. Whatever the current that you are getting here, the same current you will be getting here, same current you will be getting here. That means at all the points you will be getting the same current at all the points. Okay. Theory you can read on your own. But now our target is that we find the relation between our inversion charge and this VDS value. That you got to know one thing, that this VDS value is affecting this inversion charge. That I got to know. that my inversion charge is a function of VDS for sure. So let's try getting some relation. So let's check that out. So what we are going to see, effect of VDS on channel, that we have already seen. So now we are going to see the effect of VDS on the inversion charge. Okay. So here what we are doing, we are applying some potential which is VDS, and this our source end is grounded. This end is grounded. So all potential is being dropped across this channel only. I will call this point as x equals to 0 and I will call this point as x equals to L. Now I am defining a function called Vx, which will talk about VDS. This function will talk about VDS. Okay. So how it will talk about? Like how I can say the value of Vx at x equals to L. The value of Vx at x equals to L, like here, let's just say if VDS is 2 volt. So this point will be 2 volt. Now you know that, sir, somewhere this point will be 1.5 volt, and somewhere this point will be 1 volt, and somewhere this point will be 0.5 volt, and somewhere this point will be 0 volt. So the whole channel will be distributed from 2 volt to 0 volt. So Vx value at x equals to L is nothing but a VDS only, which is 2 volt. Now if Vx value someone asks you at x equals to 0, that will be 0 volt. If someone asks you Vx value x at x equals to L by 2, so that would be nothing but 1 volt. So did you understand what is Vx? On a very crude level, did you understand what is Vx? Sir, Vx just talk about the distribution of VDS. It is nothing but a distribution of VDS. Distribution of VDS. Say yes or no. Okay. Now when there was no VDS, or when your VDS was very low, then your inversion charge was proportional to VGS minus VT only, right? But now you can see that as you apply the VDS, the inversion charge is getting lesser, but from the drain end. Sir, I apply VDS equals to 100 volt. What will be the inversion charge at the source end? Sir, it will be the same. VDS equals to 0 volt or VDS equals to 100 volt. If I ask you the inversion charge at the source end, it will be same only, because the effect of VDS is not being, like, source end is not being affected because of the VDS, because source end will be at 0 potential only. So source end is not being affected. That means inversion charge at the source end would always remain the same, irrespective of any value of VDS. Okay, so let me erase this one first. But VDS value is strongly affecting the inversion charge at the drain end. So now when there is a significant VDS, can I write down the inversion charge in this manner? So here this was the proportionality sign. When I removed the proportionality sign, what did I write down? COX VGS minus VT W into L. So just listen to me very carefully. Can I write it down in this manner? COX VGS minus VT minus Vx W into L. Say yes or no. Is that fine for you? More the VDS value, more, if VDS value is more, then you will have more potential here. If Vx is more, this value will be more, then inversion charge will be lesser. The Vx value at x equals to 0, the Vx value at x equals to 0 will always be 0. This is always fixed. This is always fixed, and this is also always fixed. More Vx, basically more VDS, more Vx. More VDS, more Vx. If Vx is more, that means something that is being subtracted that is more, that means Qin will be less. Is that understandable to you? Can I write down this equation? A very crude way of writing down this equation, but are you able to relate it? Let's let's look at it more. At x equals to L. At x equals to L. What is the value of Vx? That is equals to VDS. So what will be your inversion charge? Sir, inversion charge would be Q in COX VGS minus VT minus VDS WL. That means at the drain end you will get the least inversion charge. What I mean to say is that at x equals to 0, and secondly, like here writing down Vx at x equals to L by 2 equals to 1 volt, that is wrong. Why is that so? This line is wrong actually, because now resistance is not uniform, no? Like here I saw, here we saw R, 2R, 3R. As you have increased the VDS value, inversion charge is getting changed. That means the resistance are also getting changed. So it's not necessary that sir, it is not necessary that at the midpoint only you will get the half voltage. So this line would be actually wrong. This line would be actually wrong. Are you able to understand this point? Because this kind of depletion region we are getting, no? On a crude way, if I show this kind of a depletion region we are getting, or inversion layer, this kind of inversion layer we are getting. So here there is less resistance, like here there is less resistance, then there is more resistance, then there is even more resistance, right? So it's not necessary that sir at midpoint only you will get the 1 volt. So this is also wrong. Showing in this manner, that is also wrong. Because previously when VDS was low, then resistance was uniform, but now it is not uniform. Here you might have R, then you are having 2R, then you are having 3R, right? Is that understandable to you? Okay, so this is wrong. We cannot write down in this manner. So basically the VDS value has become a function of x. This is what I am saying. So in a very crude way I can write down this particular thing, and at x equals to 0 the Vx value is 0 volt only. Vx value at x equals to 0 is 0 volt only. So what will be the inversion charge? That would be Cux Vgs minus Vt, and this value will be 0, W into L. So you can say that it is unchanged. And I told you at the source end nothing will change. At the source end nothing would change. Why at the source end nothing would change? Because source end is feeling 0 potential. It is having no impact of VDS. So source end will say that my charge Cux Vgs minus Vt W into L. Cux Vgs minus Vt W into L. It is unchanged. It is same as low VDS value. So are you able to like appreciate now that like are you able to satisfy yourself that sir this equation is fine? Are you able to satisfy yourself that sir this equation would work? Say yes or no. Okay. Now when VDS equals to VDS set, when VDS equals to VDS set, then Q inversion. Here also I can do one thing. Q inversion at x equals to L I should put, right? Q inversion at x equals to 0 I should put. This is your inversion charge at x equals to 0. When your VDS equals to VD set, then Q inversion at x equals to L would become 0. Say yes or no. Inversion charge at x equals to L. Inversion charge at x equals to L. Inversion charge, this is my x equals to 0. This is my x equals to L. When VD is equals to this point, pinch off point you can call it, or you can call it VD set as well. Both are the same thing for MOSFET. For enhancement type MOSFET, this is known as enhancement type MOSFET. Why it is known as enhancement type MOSFET? Because here we are enhancing the channel. Previously we started with the P type channel. We started with the P type channel. We started from here. The channel was P type. We made the channel from P type to N type. So these are known as enhancement type MOSFET. So here I will put these, whatever the discussion that we have done the discussion for enhancement type MOSFET. Enhancement type MOSFET. That means channel is getting enhanced. From P type you have made the channel to N type. Okay. Yeah, so what I was saying. So inversion charge would become 0, right? When VD set is there, the inversion charge would become 0 at the drain end. So inversion charge at x equals to L. Here your inversion charge at x equals to L has become 0. Okay. So what is your inversion charge at x equals to L? So that would be Cux Vgs minus Vt minus VDS. Vgs minus Vt minus VDS. What is VDS? VDS is nothing but VDS set, and that is equivalent to 0. Is that understandable to you? your inversion charge at x equals to L is 0, right? So your inversion charge at x equals to L is COX VGS minus VT minus VDS set. That would be equal to 0 because VDS value is replaced with VDS set now. So from here, what do you see? If you solve it, you can see that, sir, VDS set is coming out to be nothing but VGS minus VT. If I am an interviewer at IIT, I will surely ask you this characteristics, okay? And then I will ask you to explain that why this value is equal to VGS minus VT. 99% student, like I would say 99.9% student, like out of 1000 student, 999 student would simply remember that it is VGS minus VT. Why it is VGS minus VT? This is the explanation. That first you will explain that, sir, if there was no VDS, then my inversion charge was simply proportional to VGS minus VT. And this is how I can write it down if I remove the proportionality sign. But if VDS is significant enough, then from the drain end, I will start getting the depletion region from the drain end. That means my inversion charge will start getting lesser. So at the drain end, what is happening? Sir, whatever the potential that I am applying, that is directly appearing here. So at the saturation, what will happen? My inversion charge will be completely gone. So my drain potential is surely affecting the inversion charge. My drain potential is surely affecting the inversion charge. So inversion charge, which I previously wrote VGS minus VT, now I can write it VGS minus VT minus Vx, where Vx is the potential distribution of VDS. What is Vx? Potential distribution of VDS. Potential distribution of VDS. Okay. So, sir, my potential distribution of VDS is surely affecting my inversion charge. Now, at x equals to L, where my potential is VDS only, I will simply put VDS in this equation. At x equals to L, this much inversion charge I will have. Now, when I am achieving the saturation, at that particular point, my channel is completely pinched off. That means my inversion charge has become 0. So, my VD set is coming out to be VGS minus VT. There you go. Understandable? Okay. So, eventually you need to remember this one. But again, like if you know the derivation, then it will help you a lot in IIT's interview. Okay. In the interviews of IITs, it will help you a lot. Or ISC as well. So, what is the conclusion? For turning on the MOSFET, we need to apply VGS should be greater than VT and VDS should be greater than 0. For achieving the saturation, surely VGS should be greater than VT, but VDS should be greater than or equals to VGS minus VT. Or I should say, like saturation would be achieved here only at VGS minus VT. And when your VDS is greater than VGS minus VT, in this whole region you will have the saturation. In this whole region, saturation would be there. Right? You can see in this characteristics, in this whole region there is saturation. If your VDS is greater than VGS minus VT, so in the whole region you are having saturation. So at the end of the day, you just need to remember this slide, that if your VGS is greater than VT and VDS is greater than 0, your MOSFET would turn on. To achieve the saturation, VGS should be greater than VT and VDS should be greater than or equals to VGS minus VT. That means when your VDS is becoming VGS minus VT, at that time you will achieve the saturation. Current equation for linear region we have find out. What is the current equation? Sir, mu n COX W by L. You don't need to remember it. Okay? You don't need to remember it. Eventually, one equation I will tell you to remember, and that would be it. So this equation, as of now, you don't need to remember it. Current equation for linear region where VDS is significantly, VDS is very low. VDS is very low. Or you can say that VDS is much lesser than VGS minus VT. Say yes or no. Like VDS is here, this point is VGS minus VT. So VDS is much lesser than VDS minus VT. In that particular point, you are getting linear range. Now we need to derive the current equation when your VDS is significant. Previously, this was the current equation that we got. How did we get it? Sir, ID was Q inversion divided by tau. This was the function of x? No. Q inversion was not a function of x here. Here your Q inversion was not a function of x. Even this time tau was also not a function of x. But now everything would be a function of x. Why is that so? Let's check that out. So again, sir, I will write down the current. Current can never be a function of x, right? If there is a device, no matter what is happening inside the device, I don't know what is this device. What is happening inside the device, sir? Here there is also some node, I don't care. But if I current is flowing here, then here also I current would flow, here also I current would flow, here also I current would flow, everywhere I current would flow. So I current can never be a function of x, right? It can be a function of time, but it can never be a function of space. X is space, right? This is space. So current can never be a function of x. So what I will write down? So Q in x divided by 2. Q in x I already know. What is your Q in x? Sir, previously it used to be COX VGS minus VT. Previously it used to be COX VGS minus VT, but now this thing is also there. Vx thing is also there, which is disturbing our Q in, inversion charge. What about tau? Time equals to distance upon speed. Distance upon speed. Distance is L only. Like your electron needs to travel the distance of L only. Electron will be traveling the distance of L only. It will be traveling your complete channel length. It will be traveling the complete channel length, which is L. So electron needs to travel the distance of L only. So L is same, but what about Vd? So here I am putting Vdx. Why I am putting Vdx? Why is that so? Because electric field will be a function of x. Why electric field will be a function of x? Because you know that what will be your electric field? That would simply be minus dVx by dx. Let's talk about electric field more. So what is your electric field? Electric field is actually nothing but a negative gradient of the potential. So negative gradient of the potential for channel. In the channel, what all potential are present? Sir, VGS, effect of VGS will also be there, and effect of Vx will also be there. Is that clear to you? So basically in the channel, this much potential is present, no? Vt is the fixed value, I don't care about that, but channel is being affected by VGS and Vx. And why I put VGS minus Vx? Everyone can understand it. Why VGS minus Vx? Because VGS is making the inversion layer and Vx is like taking down the inversion charge. Like it is a very crude way of derivation, but this is the best possible way. That this is how I can define my electric field. Minus d by dx, VGS minus Vx, where your potential is being distributed from x equals to L to x equals to 0. At x equals to L you are having VDS, at x equals to 0 you are having 0 potential, right? Vx value, I am talking about Vx value. At x equals to L you are having Vx value, at x equals to L you are having VDS, at x equals to 0 you are having 0, but this is a function of x. VDS value is a function of x. So VGS is not a function of x, only Vx is a function of x. So as you move along the x is moving like this, x is moving like this. So with increasing x, your Vx is increasing. Is that understandable to you? That means the direction of electric field will be this. If you are not getting the direction, then simply just see that here what you will be getting, d by dx Vx. Derivation is actually not important. Eventually derivation is not important. Whatever the answer we are getting, that would be important. So from here, one thing I can see that, sir, this is the thing you are getting. So what I will see, sir, my I is, your current I is inversion charge COX VGS minus VT minus Vx W into L divided by L, and then this particular part would go upward. We are talking everything about mu n. I hope this particular step is not very confusing for you. Just remember that electric field is nothing but dVx by dx. That's it. Or you can just think that why electric field is becoming a function of x. Who is the reason why electric field is becoming a function of x? If only VDS was present, then electric field was not a function of x. But what I am saying, if VDS was low, then electric field was not a function of x. But now VDS is significantly high. So distribution of VDS has become a function of x. Distribution of VDS has become a function of x. Because of that, electric field has also become a function of x. Is that understandable to you now? I hope it is understandable. Okay. Now mu n dvx by dx. Now what I can do, I can take this dx here, I dot dx, that would be equals to mu n cux w by l. Something is wrong. Okay, mu n cux l and l is getting cancelled out. Okay, l and l is getting cancelled out. So here what you are getting, mu n cux w vgs minus vt minus vx into dvx. All good. So I dot dx mu n cux vgs minus vt into dvx minus mu n cux w vx dvx. Is that clear to you? Say yes or no. Can I take the limit of x? Integration I am doing on both of the sides from 0 to l. Mu n cux w vgs minus vt integration from 0 to l dvx minus mu n cux w from 0 to l vx dot dvx. Is that clear? So what will be this integration, sir? It will be simply be I into l, right? Because what will be the basically what will be this integration? 0 to l dot dx. Integration of dx would be x, 0 to l minus 0 will be l. What will be this integration? 0 to l dvx. So integration of dvx would be vx only from 0 to l. So v of l minus v of 0. What is the value of v of l? So that is vds. What is the value of v of 0? That is 0. So this integration is vds. What about this integration? So 0 to l vx dot dvx. The value will be vx square by 2 and limit should be put from 0 to l. So v square l by 2 minus v square 0 by 2. This value is 0. V square l is nothing but vds square. So answer would be vds square by 2. So all the integration I have solved. So what you will be getting, I into l should be equals to mu n cux w will be taking common. Will be taking mu n cux w common, right? And from here this l can come downward. This l can come downward here. So this is the I we are getting, mu n cux w by l, right? Now you open the bracket. Now in the bracket mu n cux is coming common. Vgs minus vt you are having. Vgs minus vt you are having. Then this integration 0 to l dvx. 0 to l dvx is coming out to be equals to vds minus. This has been taken common. 0 to l vx dvx, that is coming out to be vds square by 2. There you go. This is the current you are getting and we will call it drain current. Okay, we will call it drain current. This is the simplest possible derivation that you can get. If you want to avoid the derivation, you can avoid it, but again, like good intuitive derivation is there. Like I don't know from like in the gate examination how I can ask the question from here, but surely in the interview I can frame a lot of questions from here. Like about the inversion charge, I can ask you, inversion charge is not only depending on VGS, sorry, it is depending on the VDS value as well, how it is depending on VDS value. So all these things I can ask you, like at the drain and the inversion charge is getting lesser. So inversion charge is becoming 0, then from there you get this condition. Which condition? You get this condition of saturation VGS minus VT. Then how you get the current equation? So Q inversion by tau, but this is becoming a function of X. Then this is how I can write it down, and tau value also I can write down. Eventually tau is also a function of X only. This time is also a function of X. How it is a function of X, this is how I can explain. This I hope you have understood. Electric field is becoming a function of X because the potential distribution of VDS is also a function of x. That's why Ex is equals to dVx by dx. And then this is the answer we are getting. So this is eventually your current equation. When VDS is significant, but surely here your VDS is less than or equals to VGS minus VT. Sorry, less than VGS minus VT. Why is that so? Because here what do you see? As you increase VDS, like basically the current is depending on VDS, no? Here your current is function of VGS and VDS. It is a function of VGS and VDS. Say yes or no? But you know one thing. What do you know? That sir, in saturation, here in this particular region, your current is not a function of VDS. Even if you increase VDS, the current remains the same only. So in saturation, so this is the equation for, this is the scenario for linear and sublinear region, right? But your current is only a function of VGS, or you can say current is not a function of VDS when you talk about saturation region. So to get the saturation current, what you need to do? To get the saturation current, I need to find out saturation current ID set. What I need to do? In place of VDS, you put VGS minus VT. Because whatever, this is the point where you are moving from sublinear to saturation. This was your sublinear, and here you are moving to saturation. So this is the point where you are moving from sublinear to saturation. That means you can apply the equation of sublinear region at this particular point. At this particular point, you can apply the equation of sublinear region, right? So do you know the equation of sublinear region? Yes, sir. This is the equation of sublinear region. So at VDS equals to VGS minus VT. When your VDS is equals to VGS minus VT, you will attain the saturation. So here in place of VDS, what you put? VGS minus VT. So this would become VGS minus VT whole square, and this would become VGS minus VT whole square divided by 2. So VGS minus VT whole square, let us say VGS minus VT is x. So x square minus x square by 2. What that would become? X square by 2. So eventually your answer would come out to be mu n Cux W by L. Mu n Cux W by L. X square by 2. So this 2 can come here, and here you will get VGS minus VT whole square, right? Because saturation is achieved when the saturation is achieved. So saturation is achieved when your VD sat is actually equals to VGS minus VT. So saturation is achieved when you applied VDS equals to VGS minus VT. After that, the current remains same. It doesn't depend on VDS, and you can see that, sir, this current is not depending on VDS. Another thing you can see, if VDS is low, then this part will be very low. Let's just say if VDS is 0.1, then what will be its square? 0.01. It would become even lower. So this part would be very low. That means this part would be nearly 0. So this particular part would be gone. VDS square by 2 would be gone when your VDS is very low. So when your VDS is very low, the equation you will get is mu n Cux W by L VGS minus VT into VDS. Were we getting the same equation? Mu n Cux W by L VGS minus VT into VDS. When your VDS is very low. So the point is, you only remember this equation, then you will be able to write down all other equations. Is that understandable to you? What I am saying? So the equation for MOSFET NMOS current equation for linear and sublinear region is mu n Cux W by L. This is the equation I will keep in my mind. VGS minus VT into VDS minus VDS square by 2. This is the equation I will keep in my mind. For saturation region, saturation is achieved at VDS, when your VDS is equals to VDS sat, and VDS sat is nothing but VGS minus VT. So here I will put VGS minus VT. So your ID saturation current would be nothing but mu n Cux W by L here you will put VGS minus VT, and VGS minus VT whole square by 2. So x square by 2 you will get. So this part would become 2 VGS minus VT whole square. Okay. So this is the formula should be there in your mind, and this formula should be there in your mind. So this formula will go for linear and sublinear, and this formula will go for saturation. Okay. Eventually we will write down all the conclusion which should be there in your mind. So that also at that point as well we will write down the conclusion. Along with that, here I can write down that when VGS is greater than VT and VDS is greater than 0, then MOSFET turns on, right? We are mainly talking about NMOS. Substrate is P, channel is N, that's why it is NMOS. NMOS turns on, and when your VDS is greater than equals to VGS minus VT, then your NMOS goes into saturation, and when your VDS is less than equals to VGS minus VT, then your NMOS remains in linear, or here I should say less than only, linear and sublinear. Okay. And when your VGS is less than VT, what does that mean? That means that current would be 0. So your NMOS remains in cutoff. This region is known as cutoff region. When your VGS is less than VT, then there is no current flow. So it is known as cutoff region. Cutoff region, saturation region, linear region and sublinear region. Okay. Let's see what else we are having. Now we will draw the ID versus VDS plot and ID versus VGS plot. So what kind of ID versus VDS plot you are getting for a fixed VGS? For a fixed VGS, sir, this kind of plot I was getting. And then, sir, there you go. So this is a particular VGS value I am having. Let's just say this VGS is 3 volt. Now, and VGS is 3 volt, and where the saturation is achieved? Let your VT value is 1 volt. Let VT value is 1 volt. So here saturation would be achieved at VGS minus VT, that means this is 2 volt. So saturation will be achieved at 2 volt. Say yes or no. Now if I increase my VGS, what will happen? More VGS means more inversion charge. VGS is increased. Just think about the basic structure. Just think about the basic structure. More VGS means more inversion charge. More inversion charge means more current. So current will increase. Right? Along with that, my saturation voltage will also increase. Why is that so? Because what is my VD sat? My VD sat is, sir, my VD sat is VGS minus VT. So let's just say I have made my VGS equals to 4 volt. So more current, along with that I will be getting saturation point ahead. So what kind of graph I will be getting? Sir, you will be getting this kind of graph. This is the graph, so that you will be getting for VGS equals to 4 volt. Here your current saturates for VGS equals to 4 volt, and you are getting the saturation current here. Let's make it whole green only. This will be my 3 volt. Okay, VGS equals to 4 volt only I will put here. VGS equals to 4 volt only I will put here. Right? Now if VGS equals to 2 volt, for lesser VGS, the inversion charge would be lesser. If inversion charge is lesser, that means lesser current would be there. So current would also be less. Say yes or no. Current would also be less. Current would also be less. Right? This kind of characteristics you will be getting for VGS equals to 2 volt. Because VD sat would be 2 volt minus 1 volt. That would be 1 volt only. So your VD sat would be 1 volt. Here you are getting the saturation. Although this graph is yes or no. Is that understandable to you? Okay. And when VDS is 0, there will not be any current, because you know that there will be no bias. If there is no reverse bias, then there will not be any current. So this kind of characteristics you are getting. Here your VGS is increasing. As you go upward, your VGS is actually increasing. Why it is increasing? More VGS, more current. if you draw VGS ID versus VGS curve. So till the point of threshold voltage, there will not be any current. After that, the current will rise up. It is not the exponential expression, it is a random expression that we don't know. So after that, the current will rise up, right? Here you know, sir, which region is that? Like for this curve, this much region is something else, but this much region is saturation, right? And for the other curve, for the white curve, this much region is saturation, and for the green curve, this much region is saturation. Is that understandable to you? So these are the saturation line. Okay, what I can do is that I can make and I say these are the saturation region, right? And when I join these points, it will be like a parabola, which I am not able to make perfectly. So when I join these points, this kind of a parabola I will be getting. So before this parabola, the region is linear or sublinear. Linear or sublinear, right? Initially linear region is there and then sublinear region is there. So linear or sublinear region is there, which is this much of part. After that, saturation part is there. Like here, if you see, till this point you are having linear or sublinear. After that, saturation. Here till this point you are having linear, this much linear or sublinear. After that, saturation. And here till this point you are having linear or sublinear. After that, saturation, right? More VGS, more current. If VGS increases, if VGS keeps on increasing, more and more inversion charge you are having, the same thing would take place, right? Like threshold voltage is a device value, right? Threshold voltage. Do you remember the formula? Threshold voltage. So it is VFB plus under root 2 2 epsilon SI QNA 2 phi F. Although I asked you not to remember this formula. So this was the formula, this was the flat band, along with that 2 phi F. So here phi F would depend on NA and I, right? NA is fixed, Q is fixed, NSI is fixed, 2 is fixed, COX is fixed. V flat band would also be depend on the device parameters only. So it will not be changing with respect to supply. VT will always be fixed. Threshold voltage, if I am saying that device threshold voltage is 1 volt, it is fixed. Are you able to understand this point? Okay. So device threshold is fixed. Now when I am drawing ID versus VGS, then I am drawing it at a fixed VDS, right? ID versus VGS I am drawing. That means VDS I have kept a fixed. VDS is fixed. Let's just say VDS was 2 volt. So if I am increasing VGS, what will happen? More VGS, that means more current. Any expression you can see. Either you see this expression or you see this expression. Here VDS is fixed. If you increase VGS, current will be more. If you increase VGS, current will be more, right? So increasing the VGS, more inversion charge, more current you will get. It's just that I will draw 2 more plots. Okay, I will draw here 2 more plots. VT value will be same. This plot I have drawn, and another plot I will draw, which will be this plot. Okay, so this VDS we already know that this VDS is 2 volt. Here, how do I put so here I know that this VDS is 2 volt. Now one of the VDS would be 1 volt and one of the VDS would be 3 volt. So which curve? This curve is blue, this curve is maroon. So which curve will be 1 volt, which curve will be 3 volt? That you need to think. So how will you think? More VDS means more current. Say yes or no. More VDS means more current. If VDS increases, more current would be there, stronger electric field will be there. So more VDS, but till a certain point. After that, saturation would be achieved. So till a certain point, more VDS means more current, right? Now at a fixed VGS, if I fix a VGS value, let's just say here I fix this particular VGS value. I have fixed this particular VGS value. At this fixed VGS, in which condition you are getting more current? Oh, this is not how I can show it. Like how will I show it? VGS should be fixed, no? VGS should be fixed. So how will I show it? Which VDS is more, that you need to find out. Right, so how will I show it? At a fixed VGS, if I fix VGS, then where I am getting more current. Yeah. So in this scenario, I am getting this much current when VGS is fixed. In this scenario, I am getting this much current. VGS I am fixing at a particular voltage, and in this scenario I cannot even make it. So what I will do, I will make the current somewhere here. Yeah. So this VGS I have fixed. So here I am getting this much current, here I am getting this much current, and here I am getting this much current. So for the blue curve I am getting current ID1, and for green curve I am getting current ID2, and for maroon curve I am getting current ID3. You know that ID1 is more than ID2, it is more than ID3. You agree to this point? If current is more, basically at a fixed VGS value, at fixed VGS1, here you are getting very less current, here you are getting more current, and here you are getting even more current. That means VDS has to be larger, no? If more current is there, that means VDS has to be larger as well. What does that mean? That means this guy would be VDS equals to 3 volt, and this maroon would be VDS equals to 4 volt. Is that understandable to you? ID versus VGS curve. Like at a certain value of VGS, in this scenario you are getting this current, in this scenario you are getting this current, and in this scenario you are getting this current. That means at a certain value of VGS you are getting maximum current in the blue curve. Maximum current you are getting in the blue curve. What does that mean? Here VDS would be larger. So this would be 3 volt, this would be 4 volt, this would be 2 volt. All good? Right? Understandable? So all these curves are understandable. At here it is very easy that as VGS increases, my saturation point will also increase. Right? Where we are getting the saturation, that point will also increase. Along with that, current would also be more. More VDS means more current. So here I am drawing the curve of VGS versus VT. Sorry, VGS ID versus VGS for a fixed VDS. So when I kept VDS as at 2 volt, so I know that before threshold it is not going to conduct. But after threshold, here the current would be very large. Right? Here the current, in this case, current would be highest. When VDS equals to 3 volt, the current would be highest. Right? Because more VDS, more current. And here you can see that, sir, with respect to a certain VGS value, we are getting ID1, ID2 and ID3 current. ID current is the maximum. That means VDS here has to be maximum. Okay. So this is the characteristics we have seen. Now we will see the same thing for PMOS as well. Ditto same working is there. Directly we will draw the curve. Okay. And some more points we will see. I need to take a break and then I will come back. We will study about PMOS. As of now, you revise everything that you have studied here. This thing you need to remember. Basically, this slide you need to remember. This slide is important for you. This slide you need to remember, and this characteristics you need to remember. That's it. If you forget the physics, everything, no need to worry. This slide you remember, and this slide you remember. That's it. You will be able to solve most of the questions. And physics and everything I have explained. I hope you are getting a good meaning. I hope you have enjoyed the derivation as well. Like this is a different kind of derivation. You wouldn't find it at a lot of different places. I took it from Neiman only. So in Neiman, this kind of derivation is given. Okay. And Naresh Imani sir from NPTEL IIT Hyderabad, they have also taught in this manner. Okay. And talking about this band diagram thing that we explained here, this is taken from Digbijoy sir. Okay. Digbijoy sir from ISC Bangalore, EDC course is there. So he has explained in this manner. Okay. A lot of things we are taking from Karmarkar sir as well from IIT Madras. So that's the thing. Like if someone is very interested in EDC, I can tell like these many playlists you can follow. But like I am making sure that 90% of the all NPTEL content will be covered in our EDC playlist. Okay. So whatever the EDC content we are uploading, 90% of the NPTEL covered content will be covered. 10% that will be out of the gate syllabus. If you want to study, I can tell you the playlist. Like basically the playlist are from Naresh Imani sir, IIT Hyderabad. Okay. IIT Hyderabad. Okay. and Digbijoy sir. Here I should put professor and sir as well, from ISC Bangalore, and Karmarkar sir from IIT Madras. This is the oldest playlist. This is 6 years back and this is 3 years back. This is the oldest. Okay, and then this one, then this one. Like even the oldest one is like, if I need to pick one playlist like where I appreciate the most, all are like brilliant professor, like no comparison at all. But here I have found out a lot of new things when it comes to MOSFET, because MOSFETs are new technology, like when he was teaching at that particular time, MOSFETs were there, but we were not using it rigorously. As of now in the industry, we use MOSFETs rigorously. People have done enough research, they are studying about it as well. That's why in the recent playlist you would find that MOSFET is explained better in these playlists. Here MOSFET is explained but more mathematically, because this is 17 years old, right? Somewhat like somewhere in 2007 it was recorded, so it is like very old playlist. Okay, so when it comes to MOSFET, then these two playlists are very good, and other things like BJT, PN junction, like absolutely brilliant explanation in this particular playlist. So can't compare, I'm just telling that these many resources are there that from where you can actually learn EDC. Although like I'm picking everything from here only and representing in front of you. Okay, so I hope you will never ever feel like that, sir, this thing I'm missing out, that thing I'm missing out. Like in the best possible manner, like these resistance and all, in that manner we are studying. So I don't think you will have any problem at all. Okay, derivation and all, that is also clear. Everything is crystal clear to you. These curves and everything is also clear, and we will study it again in analog as well. Okay, we will study about PMOS now. Let me take a break and then I will come back. Yeah, welcome back. So we need to study about P channel enhancement type MOSFET now. PMOS we will study. Okay, so here N substrate would be there, P plus, acceptor atom doping I have done. Metal is there, oxide is there, same structure is there. Just tell me one thing, at the gate, should I apply positive bias or negative bias to turn on the transistor? Positive bias should be applied or negative bias should be applied? What I need to do? I need a layer of holes here, because this is P type, this is also P type. I need a layer of holes here, right? I need a P channel here. If I need a P channel, that means here I need to apply the negative potential, because what this negative potential would do? This negative potential would attract the holes. That means here negative potential needs to be applied. What about at the drain? At drain, what needs to be applied? What do I want? That holes should get out of here and then get into the drain. This is what I want. From the source, holes should get out. That means what should be the direction of electric field? So the direction of electric field I would want in this direction. Why is that so? Because if holes are moving in this direction, then the electric field has to be in this direction as well, because holes move in the same direction as the electric field. That means electric field should be in this direction. What does that mean? Drain has to be negative. Why is that so? Because if source is at 0 and drain is negative, then this will be the direction of electric field. 0 is greater than this negative value, right? So this will be the direction of electric field. So in the presence of electric field, if your, now what I will say, here I will talk about VSD. VSD would be positive or negative? Just tell me one thing. First let's talk about VDS. VDS would be positive or negative? VDS would be VD minus VS. VS is at 0, VD is negative. What does that mean? It would be negative. So what will be your VSD? VSD is VS minus VD. VS minus VD. VS is 0, VD is negative. Negative, it would become positive. So your VSD is positive. Similarly, your VSG is positive. You can think of it, right? VSG. Here if I write down, your VDS was negative and VGS was negative. This is the case of PMOS we are discussing. In NMOS, what was happening? Do I need to explain the working? Working I don't need to explain, right? Here sufficient enough threshold voltage, sufficient enough gate supply I will do. If I apply the sufficient enough gate supply, then inversion layer will be framed. Inversion layer will be framed. If inversion layer is framed, then if I apply negative enough, like if I apply some negative potential at the drain, then what will happen? Holes will move, current will flow. That's it. Holes are moving in this direction, so now the current would be in this direction. So current is flowing from source to drain here, right? Current is flowing from source to drain. In PMOS, in NMOS, what was the scenario? In NMOS, this was the current, right? What was the current? This was the current. So current was actually flowing from If this is your ID current, this would also be ID, this would also be ID, this would also be ID. So current was actually flowing from source to drain. Here opposite process is happening. The current is flowing from drain to source. That we will see. I will draw the diagram. This diagram I will draw. But as of now, working is clear to you. For NMOS, what was the scenario? Sir, your VDS was positive. At drain, I was applying higher potential. At gate as well, I was applying higher potential. Opposite, I don't need to think. In NMOS, I don't need to think the opposite. Right? Here, in NMOS, your VT was positive. Threshold voltage was positive. So what do you think? Here, your threshold voltage will be positive or negative? Here, your threshold voltage would be negative. In case of PMOS, threshold voltage would be negative. Let's just say threshold voltage is minus 3 volt. That means I need to apply minus 3 volt to get the inversion layer. If I am applying minus 4 volt, will I get the inversion layer? And if I am applying minus 2 volt, will I get the inversion layer? What I am saying is that my threshold voltage for PMOS is minus 3. My threshold voltage for PMOS is minus 3. So if I apply minus 4 volt at the gate, will I get the inversion layer? Or if I apply minus 2 volt, then I will get the inversion layer. I will get the inversion layer at this potential. That means if my VG is less than VT, or you can say if your VGS is less than VT, VT is minus 3. So if your VGS is less than VT, then current will be conducted. If your VGS is less than VT, then the current will be conducted. Do you agree to this point? So that point we are going to see later on, but as of now, let's just make the circuitry. What kind of circuitry we will make? This kind of circuitry we will make. Right? Drain is at negative potential than the source. Gate is at negative potential than the source. Right? So here can I write it down as VSG? Here I am writing down as VSD because source is at higher potential. And here inversion layer will also be framed. Inversion layer of holes will also be framed. Similar working, everything would be same, current equation, everything would be ditto same. It's just that we need to focus on these points. What is the point? Let's see it carefully. Basically, we need to find out the point when MOS will turn on, where your PMOS will turn on. So have some patience and keep on looking at the screen. Threshold voltage is minus 3 volt. I am assuming that threshold voltage is minus 3 volt. What will be my mode of VT? Mode of VT will be 3 volt. I will be using it somewhere. Have some patience. For the PMOS to turn on, just now I said that your gate potential should be negative. That means your VGS gate potential should be negative. Your VGS gate potential should be negative. If at the gate, if I apply minus 4 volt, my job is done. But if you apply gate potential to be minus 2 volt, your job is not done. That means if your VGS is at 0, it is less than VT, then your job is done. Is that understandable to you? So here I will write down that for PMOS to turn on, VGS equals to minus 3.1 will work. But VGS equals to minus 2.9 volt will not work. Is that understandable to you? So can I write down that my VGS is less than VT? That means minus 3.1 should be less than minus 3. Is it correct? Yes. But minus 2.9 is not less than minus 3. That means here current will not be conducted. So this is the condition we are getting. But we don't want to deal with negative sign. So can I write it down in this manner? VSG should be greater than mode of VT. There you go. Can I write it down in this manner? What will, if your VGS is minus 3.1, that means what will be your VSG? Sir, VSG would be 3.1. What is your mode of VT? Sir, mode of VT is 3. That means this equation, VSG greater than mode of VT, that holds true. Basically, sir, I will remember the condition for NMOS only. Sir, for NMOS, I remember this condition. To turn on, the condition was VGS greater than VT. So similarly, sir, for PMOS, what I will do? To turn on, condition would become, just interchange this, VGS. Here, gate will be at higher potential. So here what I will do? Source will be at higher potential. In PMOS, source will be at higher potential. So I will write down VSG should be greater than mode of VT because for the PMOS, threshold voltage will be negative. There you go. Will I be able to write down this much? Yes, sir, surely. So negative sign, positive sign, nothing I need to think. Sir, VGS greater than VT. When I go to PMOS, VSG greater than mode of VT. You will have enough practice. Don't worry, we will solve the questions as well. We will solve the assignment as well. You will have more than enough practice and you will never ever struggle in this sign and everything. Like Negative sign we have eradicated. If I am writing down VSG, I know that it will be positive because source will be at higher potential. 0 is at higher potential than this particular potential, right? So VSG should be greater than mod of VT. Similarly, here what I will write down. For saturation, this was the condition. VDS should be greater than or equals to VGS minus VT. Here I will write down VSD should be greater than or equals to VSG minus mod of VT. Can we verify it? Let's verify it. Let's just say I applied VG to be minus 2 volt. VG to be minus 2 volt and my threshold was minus 1 volt. So what will be the, or let's just say threshold, I applied VG to be minus 4 volt. VG to be minus 4 volt. So what should be your drain voltage such that you will get into the saturation mode. So that would be 4 minus 1 and minus sign would also be outside. So basically minus 4 minus of 1. So that would be minus 3. So if I apply anything less than minus 3, if I apply minus 4 as well, then also I will be in saturation. Minus 5 as well, I will be in saturation. Are you able to understand this point? So in place of writing down VGS value, I will write down VSG value. VSG value will be 4 and mod of VT value will be 1. Mod of VT value will be 1. So my VSD should be greater than or equals to 4 minus 1. That means VSD should be equals to greater than or equals to 3. So if VSD is greater than or equals to 3, that means VDS should be less than or equals to minus 3. Say yes or no. Basically, now I will draw the graph and everything would be clear. The point is, drain and source will be interchanged. Drain and source, gate and source will be interchanged. VT would be replaced with mod of VT. Here everything was positive. This was positive, this was positive, this was positive. No issue was there. But here the issue is this became negative, this became negative, this became negative. So better we write down the positive value, VSD, VSG, mod of VT. Right? So just a negative value we are replacing with positive value, nothing else we are doing. So let's draw the graph of ID versus VSG. What we are drawing? ID versus VSG. It is positive only. VSG positive. ID versus VSG. So till this mode of VT, it will not turn on. After that, it will turn on. Till this point, it will not turn on. After that, it will turn on. Just 1 second. Let's just say this was your VSD equals to 2 volt. Positive I have made because drain will be at negative potential. So VSD equals to 2 volt. So this would be VSD equals to 3 volt and this would be your VSD equals to 4 volt. Say yes or no. And what about this particular graph? So in this particular graph, what will happen? This kind of characteristics we will get because we are drawing it with respect to VSD. If your VSD is greater than 3, here what I have seen, if your VSD is greater than 3, what I have taken VSG as 4 volt and VT equals to 1 volt. This I have taken. So if VT is equals to 1 volt, mod of VT equals to 1 volt, or better I should say that your VT is equals to minus 1 volt, then your mod of VT would be equals to 1 volt. So what is the condition? That VSD should be greater than equals to VSG minus mod of VT. Mod of VT. So always I will deal in the positive values. Always I need to deal in the positive values. We will have enough practice, don't worry about it. Now if VSG you increase, that means gate voltage more and negative you are applying. So what will happen? This kind of diagram we will get, right? Saturation point will be shifted. So here we are doing VSG equals to 5 volt. So this will be 4. this value will be 2, and here your VSG would be 3 volt. VSG minus mode of VT, that would be 3 minus 1, that would be 2. So VSD should be greater than equals to 2 to get into the saturation. Is that understandable to you? Surely it is understandable, sir. No doubt about it. Okay, so everything is same. Now just for the factor, if they ask you to draw ID versus VGS, what they are asking you to draw? ID versus VGS. Gate voltage minus source voltage. Source voltage we are assuming at 0. So gate voltage I need to apply negative. Let's just say my VT value is minus 1 volt. So at gate voltage minus 1 volt, after that my transistor would turn on. If I put minus 2, then it will be on. If I put minus 3, then it will be on. VG equals to minus 1, it will be on. Minus 2, it will be on. Minus 3, it will be on. So what kind of graph you will be getting? Sir, I will be getting this kind of graph. Till this point it is not on. After that, sir, it is on like this. Other characteristics also you can see. These other characteristics also we can see. Just let me know if here VDS was minus 2 volt. So here your VDS would have been minus 3 volt. Because drain voltage is more negative. Drain voltage is more negative. That means more electric field is there. That means more current would be there. So in this case, we are getting more current, and this would have been your VDS equals to minus 1. So with respect to negative, we are drawing the graph. This time with respect to negative, we are drawing the graph. Considering VT equals to minus 1 volt. VT equals to minus 1 volt. Now here what will be the scenario? Here the graph would go somewhat like this. It's just like the mirror image graph we are getting. Okay, so what will be these points? Like here this point would be the saturation. Let's just say not able to make the graph in a better manner. Let's take this point. Right, graph is not looking that good, but still this is how we can show the saturation points. Let's show our VSG value. Let's just say here VSG was, what did we start from? Here VSG was 5 volt. So here VGS will be minus 5 volt. VGS is minus 5 volt. Here VGS would be minus 4 volt. Here VGS would be minus 3 volt. So it would occur at minus 2 volt, it would occur at minus 3 volt, and it would occur at minus 4 volt. Basically you would require VDS value to be minus 4 volt. That means your VSD would be 4 volt. So similar thing we can see here. VSD would be 4 volt. So these kind of characteristics in the examination they can make, and they will ask you what kind of device it is. So it is PMOS. It is also PMOS. Or this kind of characteristic also you can make, and they can make and ask you which kind of device it is. So you need to focus here. VSD is positive, that means drain is negative. Drain is negative, that means surely it has to be PMOS. So these kind of characteristics you will be able to make. Okay. Current equation. Can we write down the current equation as well? Surely we can write down the current equation as well. What will be the equation? Here mu p would come, right? Mu p COX W by L. Here what we used to write down? VGS. Here we will write down VSG minus mode of VT into VSG minus mode of VT. Because VT would be negative, no? That's why mode of VT. Here we used to write down VDS, but here we will write down VSD minus VSD square by 2. There you go. And what about saturation region? For saturation region, the current would be ID set mu p COX W by 2L, positive value VSG minus positive value mode of VT whole square. There you go. Both of the equation also we have written. Okay. So just write down PMOS and MOS side by side. What was the condition for NMOS? You remember the condition for NMOS? VGS less than VT, sir. Cutoff means zero current. ID equals to 0. This is the meaning of cutoff. For NMOS, for NMOS we remember the condition. For PMOS what it would be? Sir, always go positive. VSG should be less than mode of VT. VSG would be positive, yes. Mode of VT would be positive, yes. Saturation, what was the condition? Sir, VDS should be greater than equals to VGS minus VT. Here mode is required? No, everything is positive. Here also I will make everything positive. VSD should be greater than equals to VSG minus mode of VT. There you go. Positive, positive, positive. Current equation for linear and sublinear. Mu n Cux W by L. VGS positive minus VT positive. VDS minus VDS square by 2. Everything positive we are writing down. Let's write down in a better handwriting. Right, and here let's write down in better handwriting. That would be mu p Cox W by L. Positive, that would be VSG minus mode of VT into VSD minus VSD square by 2. Okay, current in saturation. Mu n Cox W by 2L VGS minus VT whole square. Mu p Cox W by 2L VSG minus mode of VT whole square. Here which guy was at the higher potential? Drain was at the higher potential, right? And here source was at the higher potential, right? Drain was positive. Here source was 0, drain was negative. So source was at the higher potential. Who was at the low potential? Source was at the low potential. And here drain was at the low potential. Here what is the direction of current flow? Here you can see in NMOS, let's see the direction of current flow. So holes were traveling in this direction. So in the same direction current would be there. So current is flowing from drain to source. In PMOS, current flows from drain to source. And in NMOS, current flows from source to drain. And you can remember in this manner, the current flows from low potential to higher potential only. No? Sorry, higher potential to low potential only. No? Let's just say there is a resistor. Here there is 5 volt, here there is 3 volt. So current will be flowing, that would be 2 by R. From high potential to low potential. Who is at higher potential? NMOS is at higher potential. So current will flow from drain to source. Arey wah. Wait a second. Source to drain. Drain to source. Yeah, drain to source. So low potential is drain. Okay. So here it is flowing from low potential to high potential. क्या हो रहा है यार ये? NMOS drain, electrons are getting in, so current is flowing like this. That means source to drain. Source to drain. PMOS. In the PMOS, holes are going like this. So current will be flowing into the drain. That means, sorry. Holes are flowing like this. So current is flowing like this. So drain to source. Drain to source. This is correct. Drain is at low potential. So here current is actually flowing from low potential to high potential. So you can't remember actually. Because in resistor what happens? Current flows from high potential to low potential. No? Okay, I was just telling a trick to remember. But that trick is not applicable. It is opposite. So just remember by the concept. Okay. N plus region is there. N region would be there. That would be NMOS. So electrons is flowing inside the drain. What is the use of drain? From the drain, charge carriers will get out. not the current will get out, charge carriers will get out. So in NMOS, who are the charge carriers? Electrons are the charge carriers. So from the drain, electrons are getting out. That means current direction would be into the drain. So from source to drain, source to drain. Drain will be at higher potential, that you know. And here drain to source, because holes are getting into the drain, that means current is getting into the drain, right? So it is going from drain to source. Is that clear? All fine? Okay. Let's see depletion type MOSFET, not very important, just on a quicker manner I will see. This kind of structure we have already seen. So what is the difference, sir? Same thing is there, source is there, body is there, G is there, gate is there, drain is there, metal, oxide, everything is same. Here we applied some gate potential to make the channel, but here channel will be already present. So we have done the doping. What I did, N plus doping I did, N plus doping I did, and here I did the doping of N as well. Here I did the doping of N as well, and I called it N channel. So already channel is present. Now just let me know one thing. Do I need to, like if I just put a drain at some positive potential, let's just say plus 2 volt, and gate is at 0 potential, will the current flow? Yes, sir. Why the current would flow? Sir, already channel is present, no? Already barrier is very less. So here diffusion would take place, and then there is high electric field. Basically, this high electric field, what this high electric field will do? This high electric field will pull these electrons, right? And the current would flow. So electrons will be pulled in this direction, current will be flowing in this direction. So even at 0 gate potential, current would flow. Even at 0 gate potential, current would flow. That means there is no control over the gate. So it's like that tap only. Here we saw the analogy of tap, no? Like you did not even turn it on, still the water is flowing. Would you want this kind of tap? No. So usually we don't use depletion type MOSFET. Without even turning it on, water is flowing. I wanted the control on gate. I'm not getting the control on gate. Without even turning it on, water is flowing. What does that mean? That means I would not want depletion type MOSFET. So it's just that for the theory purpose, I'm telling you that this is depletion type of MOSFET, but we actually don't use it. Already channel is present, no? So even if gate is 0, even if at the gate I'm applying 0 voltage, just by giving some positive supply here, electric field will be set up, electrons will be swept away, and current will flow. Now if I apply positive gate voltage, if I keep on increasing the voltage, like if I apply positive gate voltage here, then what will happen? Positive gate voltage I have applied here. What this positive voltage would do? This positive voltage will attract the electrons. It will attract the electrons. So already there were good enough electrons, more electrons are coming in because of this positive voltage. Because of this positive voltage, more electrons are coming in. Already this was N channel, more electrons are coming in, more electrons means more current. So if you increase the gate voltage, current would increase. But I want 0 current. Let's just say I want 0 current. I have fixed my drain voltage at 2 volt only. But I want 0 current now. Drain voltage is fixed, which is at 2 volt. You cannot do anything. Gate voltage, using the gate voltage, can you make the current 0? Yes, sir. What I will do? Sir, I will apply negative bias here. What this negative bias will do? Negative, 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 negative. What this negative bias will do? It will repel the electrons. It will say electrons go away. That means this channel may be depleted of charge carriers at some negative potential. I have applied so high negative potential such that this complete N channel is gone. All the electrons are gone. Now the current flow will be 0. Because if electrons are gone, that means barrier will be larger, right? From N channel to it is moving to P channel, because if electrons are going out, that means holes are increasing. So between N plus and P, the barrier would be larger. So you are making the barrier larger. If you are making the barrier larger, that means current will be reducing and at some point the current would be 0. So can you make the characteristics ID versus VGS? So at some negative potential, the current would be 0. And after that, if you keep on increasing the potential, the current will keep on increasing. Similar kind of characteristics you can get. So basically this point is known as threshold point. So threshold point for depletion type MOSFET, like threshold voltage for depletion type MOSFET and threshold voltage for enhancement type MOSFET, both are completely different. In depletion type MOSFET, what is threshold? It is the gate voltage at which the drain current goes to 0. And here what was the threshold voltage? It was the gate voltage at which the current was flowing. The current started flowing. But here at threshold voltage, the current is actually going to 0. So both are having complete different meaning. Is that clear to you? And here, if I am applying a negative potential, then channel will be uniformly depleted. It's not that it will be depleted from drain side or source side, because drain side would be depleting the channel, right? If this potential, if I keep on increasing this potential from 3 volt to, if I make it to 4 volt, if I keep on increasing this potential, then what will happen? From the drain side, channel will start getting depleted, right? Is that clear to you? But when I am applying gate potential, gate negative potential, so uniform electric field is there. Downward, uniform electric field would be there. In the downward direction, uniform electric field will be there. So channel will be depleting uniformly. And at some negative potential, the complete channel will be depleted and the current would become 0. Current would become 0. So this is known as threshold voltage, which will be negative, right? So threshold voltage for NMOS, what it is? NMOS, but depletion type. Although they will not ask depletion type MOSFET in the gate examination, but just for theory purpose we are writing down. Is that clear to you? What about ID versus VDS plot? The same kind of plot. Again, the same scenarios would take place. First, it will rise linearly. Then channel will start depleting. Channel will start depleting. And then eventually, from the drain end, it will be completely depleted and the current would saturate. And this value will also come out to be VGS minus VT only. Okay? VGS minus VT. Well and good. So, more things I don't need to tell, right? Any more things I don't need to tell. This much would be enough. Say yes or no. And if I need to make more plots, so this is happening at VDS equals to 2 volt. So this would be your VDS equals to 1 volt. And this would be your VDS equals to 3 volt. And similarly, here if I need to make more plots, you should be able to understand all these plots on your own. VDS equals to 3 volt, more drain potential, more electric field, more current, right? So VDS equals to 3 volt, this is VDS equals to 1 volt. Why this VT is same? Because VT is depending on this gate voltage, not on this drain voltage. That gate voltage, uniformly electric field will be there, which will be depleting this N channel. So this will not change. This will be the same only. Okay. Similarly here as well, these kind of loads you can get. I think that's it. 2 plots are enough. Okay. So VGS equals to, here I put 3 volt and here I put 2 volt. Okay. This graph is enough. Fine. Well and good. P channel depletion type MOSFET working is same. Just let me know one thing. To completely deplete it, first thing is that holes will be traveling in this direction. This will be the direction of drain current. To completely deplete it, what you need to do? Positive potential you need to apply, because what this positive potential will do? Positive potential will say electrons go back. Sorry, holes go back. Then this P channel will be completely depleted. Even if gate is at 0 potential, still the current would flow. Why? Because channel is already framed. So channel is already present, current would flow. To completely deplete it, I need to apply positive potential here. So what kind of characteristics you will get? If you draw ID versus VGS, that means here it will be completely depleted. So this kind of characteristics we will be getting. Similarly, ID versus VSG if I draw, then this kind of characteristics I will get. ID versus VSG. Because for completely depleting it, here I need to apply VSG. Source is at 0. Yeah. Here I need to apply positive potential. If gate is at positive potential, that means VSG would be negative, right? Vs minus Vg. If this is positive, then this would be, Vs is already 0. If this is positive, then VSG would be negative. That means VSG has to be negative to get the 0 current here. So this kind of characteristic you will get. Right? Well and good. I hope it is completely understandable. And here, these kind of characteristics you will be getting. Let's not spend much time here because it will not be asked. Characteristics may be asked, then you will be able to draw. Right? Because here drain would be at negative potential. Why drain is at negative potential? Because you want the electric field to be in this direction. If I want the electric field to be in this direction, this has to be negative. 0 means positive, negative means negative only. So electric field should be in this direction. So drain has to be negative. That means VDS has to be negative. So VDS has to be negative to get the current flow. And VSD would be positive. So this would be the characteristics that you will get. Okay. There you go. It is completed. So enhancement type and depletion type MOSFETs are completed. Basic introduction you have understood. Well and good. Okay. Now I will add up a video from analog lectures, because the next part that we are going to study, whatever the next part in MOSFET that we are going to study, that's actually a part of analog. That's actually a part of analog. Okay. But if I see the PYQ book, in PYQ book, a lot of questions have been put from MOSFET in EDC itself. The questions are asked on analog, but it has been put in EDC. So we will study those concepts in EDC as well, but I will directly take the video from analog and put it there. Okay. So you are going to see what you are going to see. Most important concept you are going to study channel length modulation there. Then you will study about transconductance. Okay. You will see the circuit symbol. Like we have studied PMOS and MOS. We have studied PMOS and MOS, but how would you show it in the circuit? So circuit symbol also you will see. Right? And some important questions you will see that, like why oxide layer has to be there. Why oxide layer? And when we use it as an amplifier, why we use it in enhancement mode? Like I'm saying that enhancement is more important. Why it is more important? Why it is more important? Because here control is over the gate, no? Look, in enhancement mode, the control is over the gate, no? Like gate is controlling. If gate was 0, then there was no current. Right? So 0, if gate was at 0 potential, there was no current. But here, even if gate is at 0 potential, even if you don't apply any bias, still there would be some current. And that is something that I don't want. I want my control to be over the gate. So I wanted the control over the gate. That's why I will use enhancement type MOSFET for amplification. More like better understanding you will get in analog only. But as of now, on a top level, you will understand here. Okay. What is the use of oxide layer? These questions we will see. Along with that, we will solve some questions as well. Assignment would be there. Problem solving would be there. Questions would be there. So these things you are going to watch in the next lecture. Okay. So somewhat around 3 hour 20-minute video would be there. So you would understand all these things. And then we will talk about the known idealities. So after that, what we need to discuss? We need to discuss body effect. We need to discuss subthreshold conduction. Subthreshold conduction. And then we need to study mobility degradation. Mobility degradation. Okay. So these 3 topics are like the known idealities. And some short channel effect also we can see. Short channel effect. What is the meaning of short channel effect? That means this length L is small. Length L is small. So these also we can see. Okay. So these we are going to see in the last lecture. Along with that, we will solve a good question as well, which was asked from MOSCAP. From MOSCAP, one question is there, which I forgot actually. P plus polysilicon is used, N plus polysilicon is used. So this question also we will see. One good question. So this will be your last video, 3rd video. This is your 2nd video that you are going to watch as of now. Okay then? Yeah. Thank you very much. Happy learning. Hi everyone, before starting any other video, like this was a clear brain fade movement from my end. So I need to remove this blunder here. Like when we measure the current, we measure from the inside of the MOS. Like let's talk about NMOS. When I talk about NMOS here, what was the diagram? This was the diagram. So here I said that current is flowing from source to drain. That was a big blunder from my end. Inside the MOS, the current is flowing from drain to source, no? Inside the MOS. If electrons are flowing in this direction, then this is the direction of current. So whenever I say current is flowing from drain to source, that means inside the MOS I am talking about, not outside the MOS. That is like, that was a big blunder from my end. Not from the battery, inside the MOS. So always inside the MOS it is written. So inside the MOS, the current is flowing from drain to source. That was a like very silly error. This should not have happened, right? Because it is pretty obvious that like in analog electronics we study like 1000 times that the current is flowing from drain to source for NMOS, but here big blunder from my end, and here it would be from source to drain. Okay, for PMOS it would be from source to drain. Always current will always flow from high potential to low potential only. High potential to low potential. Here higher potential is PMOS, high potential to low potential, high potential to low potential. So when we talk inside the MOS, right? Here drain to source, but inside the MOS, this is how the current would be flowing, no? If holes are flowing in this direction, so this is how the current would be flowing. So this is the direction of current inside the MOS. So where I am writing down. So here I am writing down for inside MOS. Inside MOS. Inside MOS. Okay. So inside the MOS, the current is flowing from source to drain for PMOS and drain to source for NMOS. You will remember always current will flow from higher potential to the lower potential. Higher potential in case of NMOS will be drain and lower potential will be source. And here in case of PMOS, higher potential will be source, lower potential will be drain. You will be able to remember in a very easy manner. Negative potential you need to apply in case of PMOS, positive potential you will apply in case of NMOS. In NMOS you will be having N plus substrate and your channel would be N type. In PMOS you will be having P plus substrate and your channel would become P type, right? But the substrate would be N type and here substrate would be P type, right? So to get the inversion layer of N type, what you need to do? Here you need to apply positive potential, here I need to apply negative potential. Negative potential, drain will also be negative. So drain would be at lower potential, source will be at higher potential. Here drain will be at higher potential, source will be at lower potential. Current flow inside the MOS always from higher potential to the lower potential. Drain to source, source to drain. Okay, so this was a big blunder from my end which I need to improve. So that I have improved here. So let's move to the next lecture now.